Hey guys, tonight we begin a journey back in time, back almost 2,000 years, to walk in the footsteps of someone whose work you've probably never heard of, but whose legacy touches your life every single day. I want you to get really comfortable right now. Where are you right now? Are you tucked in bed, maybe with your headphones in, the world outside finally quiet? Or perhaps you are sitting in a chair wrapped in a blanket, watching the last light fade from the sky. Wherever you are, I want you to dim those lights, get comfortable, and let yourself sink into this story. Take a deep breath. Let the tension of the day just melt away, because tonight we're not rushing anywhere. We're going to take our time walking through the life of a man who lived in ancient Rome, a man who solved problems so vast that they would make modern engineers pause in respect. His name was Marcus Vitruvius Aquilo, and he was a water engineer. Now, I know what you might be thinking, water engineer. That doesn't sound particularly exciting. But what if I told you that this man and men like him kept an empire alive? What if I told you that without the work they did, Rome, the greatest city the ancient world had ever seen, would have collapsed into disease, chaos, and death? What if I told you that at its peak, Rome consumed more than 1.1 million cubic meters of fresh water every single day, more water than many modern cities use today, and they did it without electric pumps, without computers, without any of the technology we take for granted? What if I told you that to achieve this, Roman engineers built structures so precise that they maintained a gradient of just 0.22% over distances of more than 90 kilometers? Think about that for a moment. They had to lower the elevation of their water channels by just 22 centimeters for every 100 meters of distance, and they had to maintain this precision for mile after mile, through mountains, across valleys, underground and overground. They did this with hand tools, with their eyes, with instruments that seem absurdly simple compared to our laser levels and GPS systems. And they did it so well that some of their aqueducts are still standing today, nearly 2 millennia later, monuments to human ingenuity and determination. Now, here is what really gets to me. We know the names of the emperors. We know the names of the generals who conquered lands and the senators who made laws. But the engineers who actually kept the empire functioning, most of them are lost to history. We know they existed. We know what they accomplished. But their individual stories, their fears and hopes and dreams, their moments of triumph and heartbreak, those are mostly gone, except through the fragments that remain, through the technical manuals they wrote, through the inscriptions carved in stone, through the archaeological evidence of their work. We can piece together what their lives must have been like. And that is what we're going to do tonight. Tonight I am going to take you inside the life of Marcus Vitruvius Aquilo. Now, I should tell you Marcus himself is a composite, a reconstruction, based on everything we know about Roman water engineers, but every detail of his story is rooted in historical fact. Every challenge he faces, every technique he uses, every decision he makes is drawn from the real experiences of the real men who designed, built, and maintained the 11 major aqueducts that fed Rome. We're going to follow Marcus from his youth, when he first fell in love with the mysterious art of making water flow uphill and down, through his apprenticeship, through his first assignments, through his greatest triumphs and his darkest moments, all the way to his final years when he passes on his knowledge to the next generation. Along the way, we're going to explore the actual technical details of Roman aqueduct engineering. We're going to understand how they surveyed routes with their chorobates and their librae, how they calculated flow rates, how they excavated tunnels through solid rock, how they built those magnificent stone arcades that still grace the Italian countryside. We're going to meet his team, the surveyors and architects and foremen and common labourers who turned his vision into reality. And we're going to confront the human cost of these projects, because building aqueducts was dangerous work, and men died doing it. But this isn't just a history lesson. This is a bedtime story, And bedtime stories are meant to do something special. They're meant to transport you, to help you shed the worries of your day, to give you something to think about as you drift off to sleep. So we're going to take our time with this. We're going to really sink into the sensory details, the sights and sounds and smells of ancient Rome. We're going to feel what Marcus felt, fear and pride and exhaustion and satisfaction. And we're going to connect his world to ours, because the truth is, the challenges he faced aren't that different from the challenges we face today. The technology changes, but the fundamental questions remain the same. How do we build infrastructure that will last? How do we balance immediate needs against long-term sustainability? How do we manage massive projects with thousands of workers? How do we maintain aging systems while planning for future growth? Sound familiar? It should, because these are the same questions our engineers are asking right now, today, in cities all around the world. So settle in, get really comfortable, let yourself relax, and let's begin at the beginning, in the year 47 AD, in a small town 20 miles north of Rome, where a boy named Marcus is about to discover his life's calling. Marcus Vitruvius Aquilo was born in the spring of 47 AD in the town of Vade, one of the old Etruscan settlements that had long since been absorbed into the Roman sphere. His father was a stonemason, a man who worked with his hands, cutting and shaping the tufa stone that was quarried from the hills nearby. His mother had died when Marcus was only 3 years old, something that happened all too often in the ancient world, and so Marcus was raised primarily by his father and his father's sister, his Aunt Claudia, a sharp-tongued woman who ran a small bakery near the Forum. Marcus's childhood was, in most ways, unremarkable. He played with the other boys in the streets, getting into the usual scrapes and adventures. He learned to read and write at a small school run by an aging Greek freedman, unusual for a boy of his class, but his father had insisted on it. "You work with stone, you need to read plans," his father would say. "You work with people, you need to write contracts. Knowledge is a tool, boy, same as a hammer or chisel." Marcus didn't particularly enjoy school, but he dutifully learned his letters and his numbers, not realizing yet how crucial this foundation would become. The turning point in Marcus's life came when he was 12 years old, in the summer of 59 AD. There was a problem with the local water supply. Veii was served by a modest aqueduct that brought water from springs in the hills, nothing compared to the grand aqueducts that served Rome itself, but vital nonetheless. For weeks the flow had been diminishing, and now several of the public fountains had gone dry. The town council, alarmed, sent word to Rome requesting assistance, and Rome, in turn, dispatched an engineer from the office of the Curator Aquarum, the superintendent of aqueducts. The engineer's name was Lucius Petronius Marcellus, and he arrived in Veii on a hot August morning, accompanied by 2 assistants and a wagon full of equipment. Marcus's father was hired to assist with whatever repairs proved necessary, and Marcus, curious and bored with the summer heat, tagged along. What happened over the next 10 days changed the course of Marcus's life. He watched in fascination as Petronius and his team systematically investigated the problem. They didn't just look at the obvious places. They walked the entire length of the aqueduct, all 16 kilometers of it, examining every section of channel, every inspection shaft, every settling tank. Marcus followed them, keeping quiet, staying out of the way, but watching everything. He watched as Petronius used an instrument called a corrobate, a long wooden frame with a water trough on top, to check the gradient of the channel. He watched as they lowered themselves into the dark tunnels that carried water through the hillsides, moving carefully through the waste, deep flow, their oil lamps flickering in the damp air. He watched as they took measurements, called out numbers to each other, argued about calculations, and he watched when they finally found the problem. A section of the channel wall had cracked, probably due to ground settling, and water was leaking out through the fracture, seeping into the earth rather than continuing down to the town. By the time the water reached Veii, more than half the original flow had been lost. The repair itself was technical but not especially dramatic. Marcus's father and 3 other masons, working under Petronius's direction, carefully cut away the damaged section of the wall and replaced it with new stone, sealing the joints with a special waterproof mortar that Petronius called opus signinum, made from crushed pottery mixed with lime. Within 2 days of completing the repair, the fountains of Verhaert were flowing again at their full strength. But what stuck with Marcus wasn't the repair itself. It was something Petronius said to him on the last day as they were packing up the equipment. Marcus had been watching them disassemble the chorobate, studying how it was put together, and Petronius noticed his interest. "You like this work, boy?" Petronius asked. Marcus nodded, suddenly shy. "I like figuring things out," he said. "I like how you found the problem." Petronius smiled. "That is the heart of engineering," he said. "Any fool can build something when everything goes right. The real skill is in understanding how things work well enough that when they go wrong, you can figure out why. Water is tricky, boy. It seems simple, but it is not. It flows downhill, yes, but the devil is in the details. How fast does it flow? How much erosion does it cause? How do you keep it clean? How do you maintain a steady supply for 1 million people who need it every single day? These are complex problems, and solving them requires knowledge of mathematics, of materials, of geology, of hydraulics. It requires careful observation and clear thinking. It requires patience." He paused, studying Marcus's face. "How old are you, boy?" 12, sir." "Can you read and write?" "Yes, sir. My father made me learn." "Good. You know, we're always looking for apprentices in Rome. Smart boys who can learn the work. If you are interested, if your father would permit it, I could arrange it." Think about that for a moment. Here is Marcus, a 12-year-old boy from a small town, the son of a stone mason, and suddenly he is being offered an opportunity to enter a profession that sits near the very top of Roman society. Engineers were respected. They were well paid. They worked on projects that affected the lives of millions. This wasn't just a job offer. This was a chance at a completely different life. Marcus's father, when Petronius approached him, was initially hesitant, sending his only son to Rome to live and work there. It was a big step, but he was also a practical man, and he recognized opportunity when he saw it. "You'll work hard," he told Marcus that evening. "You'll do exactly what they tell you. You'll learn everything they teach you, and you'll make me proud. Understand?" Marcus understood. 3 months later, in November of 59 AD, just after his 13th birthday, Marcus Vitruvius Aquilo arrived in Rome to begin his apprenticeship in the office of the Curator Aquarum. The Rome that Marcus entered in late 59 AD was a city of contrasts, so stark they could make your head spin. It was the largest city in the world, home to somewhere between 800,000 and 1.2 million people, depending on which modern estimate you believe. According to Dr. Walter Scheidel from Stanford University, Rome at its peak represented the largest concentration of human beings that the world had ever seen up to that point, and it wouldn't be matched again until London in the early 19th century. The city sprawled across its 7 hills and the valleys between them, a chaotic mixture of stunning marble temples and monuments, solid brick apartment blocks called insulae, narrow winding streets that had grown organically over centuries, and the occasional broad avenue that had been imposed on the urban fabric by imperial decree. The contrast between rich and poor was extreme. In some neighbourhoods, you had elegant townhouses with interior courtyards and private bathrooms. In others, you had tenements 6 or 7 stories high, where multiple families crowded into single rooms, where fire was a constant danger, where disease spread quickly, where chamber pots were emptied out of windows into the streets below, and through it all flowed water. Water was Rome's lifeline, the essential infrastructure that made urban life on this scale possible. By 59 AD, 9 major aqueducts served the city, bringing water from springs and rivers in the surrounding hills. The Aqua Appia, the oldest, built in 312 BC, the Aqua Annio Vetus, the Aqua Marcia, Rome's longest, and one of its most important, 91 kilometres from source to city, the Aqua Tepula, the Aqua Julia, the Aqua Virgo, the Aqua Alciatina, the Aqua Claudia, magnificent and brand new, completed just 11 years earlier, and the Anio Novus, the highest and newest of them all. These aqueducts together brought more than 1 million cubic meters of water into Rome every day. Think about that. 1 million cubic meters. That is about 264 million gallons, if you are more familiar with that measurement. For a city of roughly 1 million people, that worked out to about 260 gallons per person per Dalton Yoy. Now, to put that in perspective, the average American today uses about 80 to 100 gallons of water per Dalton Yoy for all purposes: drinking, cooking, bathing, laundry, toilet flushing, lawn watering, everything. Ancient Romans used more than twice that much. Why? Well, it wasn't all for personal use. Much of it went to public baths, those grand social institutions where Romans gathered to exercise, bathe, socialize, and conduct business. The imperial baths could accommodate thousands of people at once, and they required enormous amounts of water, constantly flowing in and constantly draining out. Water also flowed continuously through the public fountains that dotted every neighborhood, providing free water to anyone who needed it. It flowed through the elaborate decorative fountains called nymphia that graced public spaces. It flowed through the homes of the wealthy, who paid for the privilege of a private connection, and it flowed through the city's drainage system, constantly flushing the sewers, carrying waste away to the Tiber. According to Professor Trevor Hodge from Carleton University, one of the world's foremost experts on Roman aqueducts, this continuous flow system was actually remarkably sophisticated from a public health standpoint. Unlike systems that stored water in cisterns where it could stagnate and breed disease, the Roman system kept water constantly moving, fresh water in, waste water out, all day, every day. It was this infrastructure, more than anything else, that made Rome possible. And it was this infrastructure that Marcus was now going to learn to maintain and expand. The office of the Curator Aquarum was located on the Aventine Hill, in a large building that had once been a wealthy merchant's house, but had been repurposed for administrative use. When Marcus first walked through its doors, he was overwhelmed. There were dozens of people working there, clerks copying documents, architects bent over plans, senior engineers arguing about technical details, messengers coming and going with reports from the various aqueduct stations scattered around the city and the countryside. Marcus was assigned to sleep in a small room on the upper floor that he shared with 3 other apprentices. 2 of them were about his age. 1, a year younger. Their names were Gaius, the son of a military engineer who had died in Britannia, Titus, whose father was a surveyor, and young Decimus, the youngest at 12, who had been sponsored by a wealthy patron after showing unusual mathematical aptitude. These 3 boys became Marcus's constant companions over the next several years. Together they learned the fundamentals of their trade. Their primary instructor was a senior engineer named Sextus Favonius Priscus, a man in his late 50s who had spent his entire adult life working on aqueducts. Priscus was demanding and sometimes harsh, but he was also genuinely devoted to teaching. He understood that the knowledge he carried was precious, that it had been accumulated over centuries of trial and error, and that it was his responsibility to pass it on accurately and completely. The apprentice's education was both theoretical and practical. In the mornings, they studied mathematics, learning to calculate areas and volumes, to work with ratios and proportions, to understand the geometry of arches and vaults. They learned to read technical drawings, and eventually to create them. They studied the properties of different materials, learning which stones were suitable for which purposes, how lime mortar was made, and how it set, what made opus signinum waterproof, how lead pipes were cast and joined. They read from the works of earlier engineers and architects, particularly the writings of Marcus Vitruvius Pollio, the famous architect and engineer who had lived during the reign of Augustus. It was from Vitruvius Pollio that Marcus Vitruvius Aculo had received his middle name. a common practice for families who wanted to honor respected figures. In the afternoons, they went out into the field. They visited the various aqueducts, learning to recognize the subtle signs that indicated problems developing. A slight green discoloration on the stone that suggested water was seeping through a joint. A change in the sound of flowing water that indicated a partial blockage. The smell of stagnant water where there should be fresh flow. They learned to use the surveying instruments, the chorobate for establishing horizontal levels, the libra for measuring elevations, the groma for laying out right angles. They practiced again and again, because precision was everything. A gradient too steep and the water would flow too fast, eroding the channel. A gradient too shallow and sediment would settle out, gradually clogging the channel. You needed that sweet spot, usually between 0.2 and 0.3%, about 2 to 3 meters of drop for every kilometer of distance. And you needed to maintain it consistently over distances that could stretch for dozens of kilometers. They also learned about the social and administrative side of the work. Aqueducts weren't just technical challenges, they were public infrastructure, which meant they were inherently political. They learned about the laws governing water use, the fees charged for private connections, the fines levied for illegal taps. They learned how to manage work crews, how to deal with contractors who cut corners, how to write reports for officials who might not understand technical details but who controlled the funding. They learned that an engineer's job wasn't just to understand water and stone and mathematics. It was also to understand people, politics, and money. According to Dr. Philip Kay, who has studied Roman public contracting and labour management, major aqueduct projects involved incredibly complex logistics, coordinating the work of thousands of labourers, dozens of specialised contractors for different types of work, and careful sequencing of operations so that materials and workers were available when and where needed. Managing a project like this required skills that went far beyond engineering in the narrow sense. It required the ability to plan, to organise, to communicate clearly, to solve problems on the fly, to make decisions with incomplete information, and to take responsibility when things went wrong. Marcus proved to be an excellent student. He had a natural aptitude for mathematics, and he loved the puzzle-solving aspect of the work. More than that, he had patience and attention to detail. He didn't rush through calculations. He double-checked measurements. When something didn't make sense, he asked questions until he understood it. Priscus noticed, and increasingly gave Marcus more challenging assignments. By the time Marcus was 16, he was regularly accompanying senior engineers on inspections, not just watching anymore, but actually contributing observations and suggestions. By 17, he was trusted to supervise small repair projects, managing teams of workmen to fix cracked channels, clear blockages, replace worn sections of pipe, and by 18, in the year 65 AD, he was promoted from apprentice to junior engineer, with a salary of 6,000 sesterces per year. It wasn't a fortune, not by any means, but it was a solid middle-class income, enough to live independently, to rent a small apartment, to feel like he was genuinely making his way in the world. Think about that for a moment. 6 years of intensive training, from age 13 to 18, before he was trusted to work independently even on minor projects. This wasn't casual labour. This was a highly skilled profession that required years of education and supervised experience. And Marcus was still just at the beginning of his career. The real tests, the real challenges were still ahead of him. What really gets to me about this period in Marcus's life is how it mirrors what we still see today in technical professions. The years of education, the apprenticeship under experienced mentors, the gradual increase in responsibility as skills are proven, the combination of theoretical knowledge and practical experience, the importance of attention to detail. We like to think of ourselves as so much more advanced than the ancient world, and in many ways we are. But the fundamental process of learning a complex skill, that hasn't changed. It still takes time. It still takes dedicated teachers. It still takes a student who is willing to work hard and learn from mistakes. Marcus's real education, though, His transformation from a competent junior engineer into someone who truly understood the art of aqueduct engineering at the deepest level began in the spring of 66 AD, when he received his first major solo assignment. The Aqua Marcia was in trouble. The Aqua Marcia was one of Rome's most important aqueducts, and certainly one of its most impressive. It had been built way back in 1944 BC, which meant it was more than 200 years old by Marcus's time. It was Rome's longest aqueduct, running 91.33 kilometers from its source at Springs in the Anio Valley all the way to Rome. For most of that distance, it ran underground, through tunnels and covered channels, protected from contamination and evaporation. But in several places, especially as it approached the city, it emerged onto magnificent stone arcades, tall arches marching across the landscape, the water channel riding high above the ground. The Marcia was prized not just for the quantity of water it brought, about 190,000 cubic meters per Dalton Y, but for its quality. The water from those springs was cold, pure, and delicious, considered the best drinking water in Rome. According to the naturalist Pliny, writing around this same time period, the Marcia's water was so good that it was specifically reserved for drinking, while lesser quality water from other aqueducts was used for baths and other purposes. But now, in the spring of 66 AD, there were problems. The flow rate had been declining for months. Sediment was building up in the settling tanks. There were reports of leaks in multiple locations, and most worryingly, the quality of the water had deteriorated. It was no longer as clear and cold as it should be, suggesting that contamination was entering the system somewhere. The curator aquarium at this time was a man named Marcus Cus Nerva, who would later, much later, become emperor. He was concerned enough about the Marcia's problems that he wanted a complete inspection of the entire aqueduct from source to city. This was a massive undertaking, 91 kilometers, most of it underground, and he wanted it done thoroughly, which meant walking the entire length, examining every accessible section, documenting every problem found. He assigned 2 engineers to the task. One was Aulus Fabricius Veiento, a senior engineer with 30 years of experience. The other was Marcus Vitruvius Aquilo, age 19, junior engineer. It was a test, obviously. Nerva and Priscus, who had recommended Marcus for the assignment, wanted to see how he would handle significant responsibility. Veiento, for his part, was not particularly pleased to be saddled with a teenage assistant on what promised to be a long, dirty, uncomfortable job, but he was professional enough to keep his reservations to himself, at least initially. They set out on a morning in late March, when the weather was beginning to warm but the heat of summer hadn't yet arrived. With them went 4 assistants who would handle measurements and note-taking, and a pack mule carrying their equipment, food, and camping gear. The plan was to start at the source and work their way down to Rome, a journey that would take at least 2 weeks, possibly longer depending on what they found. The springs that fed the Aqua Marcia were located in the hills about 40 kilometers east of Rome, in beautiful country, green and rolling. Marcus had been out to this area once before during his apprenticeship, but he'd never walked the entire length of an aqueduct, and he was both excited and nervous. The first few days went smoothly. They inspected the spring houses, the structures built around the sources to collect the water cleanly and prevent contamination. They checked the primary settling tanks, where sediment and debris were supposed to settle out before the water entered the main channel. They walked the first several kilometers of channel, which here ran mostly underground, accessed through vertical shafts, spaced every few hundred meters. The work was physically demanding. To inspect the underground sections, they had to climb down the shafts on wooden ladders, sometimes descending 20 or 30 meters into the earth, then wade through the channel itself, bent over because the ceiling was low, the water flowing around their legs, their oil lamps providing the only light in the darkness. It was cold and wet and uncomfortable, and Marcus quickly developed a deep appreciation for just how much maintenance these structures required. According to Dr. Lynn Lancaster, who has studied Roman construction techniques extensively, The tunnels of Roman aqueducts were typically about 2 meters high and anywhere from 45 centimeters to 1 meter wide, just large enough for a worker to move through them. The walls and ceiling were sometimes lined with stone or waterproof mortar, sometimes simply cut through solid rock. Working in these confined spaces in the dark, in cold water, required a special kind of toughness. It wasn't glamorous. It was hard, uncomfortable, sometimes dangerous work, but it was absolutely necessary. Without regular inspection and maintenance, problems could develop that would eventually cause catastrophic failure. About a week into the journey, they found the first major problem. They were inspecting a section where the aqueduct passed through a hillside in a tunnel about 800 meters long. As they worked their way through it, Vanto suddenly stopped, holding up his hand for silence. "Listen," he said. Marcus listened. Over the sound of flowing water, he could hear something else, a different sound. Water falling, dripping. "There," Vanto said, pointing to the tunnel ceiling. "See that?" Marcus looked up. There was a dark stain on the rock, and water was indeed dripping from a crack. Not a lot of water, but steady. "This is bad," Vanto said grimly. "This is very bad. That water is coming from above, which means there is another water source up there, probably a small spring or underground stream that we didn't know about when this tunnel was cut. It is seeping through the rock and contaminating our channel." "Can we seal it?" Marcus asked. Vanto shook his head. "Not from inside. We'd need to excavate from above, find the source, divert it. Major work. Make a note of the location. We'll need to come back with a full crew." They found 3 more such contamination points in that tunnel alone, and several more in other sections over the next few days. This explained the deterioration in water quality. The pure spring water was being diluted with groundwater from unknown sources. But contamination wasn't the only problem they found. In several locations, they found evidence of illegal taps. Someone, probably local farmers, had broken into the channel and installed pipes to divert water for their own use. This was a serious crime. Water theft from the aqueducts carried a fine of 10,000 sesterces, a crushing sum for most people. But enforcement was difficult, especially in remote areas, and the potential benefits were enormous if you could get away with it. Free water for irrigation could make the difference between a successful harvest and a failed one. Each illegal tap they found, they documented carefully, noting the location so that officials could follow up. They also physically blocked the taps as best they could, though they knew determined thieves would probably just make new ones once they left. By the time they reached the section where the aqueduct emerged onto arcades for its approach to the city, they had documented more than 40 separate issues requiring attention. Some were minor, cracks that needed sealing, deposits that needed cleaning, but several were major, requiring significant repairs. Vanto was satisfied with Marcus's work. The young man had proven himself to be thorough, uncomplaining despite the difficult conditions, and good at spotting problems. On their final evening before returning to Rome, as they sat by their campfire, Vanto said something that Marcus would remember for the rest of his life. "You know what the hardest part of this job is?" Vanto asked. "It is not the mathematics, though that takes skill. It is not the physical difficulty, though that can be brutal. The hardest part is the time scale. We build things that have to last for generations. We maintain things that were built by people who died before we were born. And we have to think about people who haven't been born yet, who will depend on this infrastructure long after we're gone. That is a heavy responsibility, boy. The decisions we make, the quality of work we accept or reject, the maintenance we perform or defer, those decisions will have consequences that ripple forward through time. You understand?" Marcus nodded slowly. He did understand, or at least he was beginning to. Think about that concept for a moment. Infrastructure that lasts for generations. Decisions made by one generation that affect the next and the next and the next. Sound familiar? It should. We're living right now with infrastructure that was built 50, 70, 100 years ago. Roads, bridges, water systems, electrical grids, all built by people who are mostly gone now. And the decisions we make now about what to build, what to maintain, what to let decay, those will affect people who won't be born for decades. It is the same responsibility, the same long-term thinking that Marcus was learning about in 66 AD. When they returned to Rome and filed their report, Nerva was both pleased with the thoroughness of their work and alarmed at the extent of the problems they'd found. He immediately authorized a major repair project, allocating a budget of 200,000 sesterces and assigning a team of 50 workers. And he put Marcus, along with Veiento, in charge of overseeing the repairs. Over the next 8 months, from summer of 66 AD through early spring of 67 AD, Marcus learned what it meant to actually manage a construction project. It wasn't enough to know what needed to be done. You had to organize crews, ensure materials were available when needed, deal with contractors who were trying to cut corners to maximize their profit, handle unexpected problems that arose, keep the work on schedule and on budget, and maintain safety as much as possible. That last point, safety, was something that weighed heavily on Marcus. Construction work in the ancient world was dangerous. There were no safety regulations, no hard hats, no insurance, no OSHA inspectors. Men worked on tall ladders and scaffolding without full protection. They excavated trenches that could collapse. They used sharp tools and heavy materials. Accidents happened regularly, and when they did, there was no medical care to speak of beyond basic first aid. A serious injury usually meant disability or death. During the 8 months of the Marcia repair project, 3 men died. One fell from scaffolding while working on an arcade repair, dropping 12 meters to the ground below. He died instantly. Another was killed when a block of stone being lifted by a crane slipped and crushed him. The third died from infection after a minor cut on his hand turned septic. Each death hit Marcus hard. He felt responsible, even though logically he knew that accidents were an inevitable part of construction work. He tried to implement what safety measures he could, insisting on proper bracing for trenches, requiring workers on ladders to have assistants steadying them, checking rigging before lifts. But there were limits to what he could do within the constraints of Roman technology and social attitudes. According to Professor Roger Ulrich, who has studied Roman construction methods, the Romans were actually quite sophisticated in some aspects of construction safety, using careful engineering to minimize risks where possible. But they also accepted a level of risk that would be completely unacceptable today. Life was cheaper in the ancient world. Workers were replaceable, and everyone, workers included, simply accepted that dangerous work would claim lives. It was the price of building great things. Marcus never fully accepted that. Each death troubled him, stayed with him. Years later, he would still remember their names. Titus Valerius, the man who fell; Lucius Didius, crushed by the stone; Marcus Nonius, dead from infection. He would remember their faces, their families' grief, and he would spend the rest of his career trying to find ways to make the work safer, even if only marginally so. But the project was ultimately successful. By early spring of 67 AD, all 40-plus issues they had documented were resolved. The contamination sources were found and diverted. The illegal taps were blocked, and the perpetrators fined. Cracks were sealed. Deposits were cleaned. When they measured the flow rate after the repairs were complete, the Marcia was delivering 204,000 cubic meters. Per Dalton Y, actually more than it had been designed for, because some of the original flow restrictions had been cleared. The water quality was back to its pristine standard, cold and clear and pure. Nerva was delighted. He wrote a commendation for both Veiento and Marcus, and he marked Marcus as someone to watch, someone with real potential. For Marcus, now 20 years old, this first major project had been transformative. He had proven himself, not just in theory but in practice. He had managed real workers doing real work under real constraints. He had faced genuine problems and solved them. He had felt the weight of responsibility when men under his supervision died. He had experienced the satisfaction of seeing a critical piece of infrastructure restored to full function, knowing that hundreds of thousands of people would benefit from his work, most of them never knowing his name or anything about the effort that went into maintaining the systems they depended on. And that was fine. Marcus was beginning to understand that this was what the job was about. Not glory or recognition, but the quiet satisfaction of keeping essential systems functioning. It was work that mattered, even if it was mostly invisible. Over the next several years, Marcus's career continued to advance. He worked on a variety of projects, some repair and maintenance like the Marsha project, others involving new construction and expansion. He developed a reputation for thoroughness and reliability. If Marcus was assigned to a project, people knew it would be done right. He also continued his education, studying not just the practical aspects of engineering, but also the theoretical foundations. He read everything he could get his hands on about hydraulics, about the behavior of water in channels and pipes, about flow rates and pressure, about the mathematics of arch construction. According to Professor Norman Smith, a historian of technology who studied pre-industrial water supply systems, the Romans had developed a remarkably sophisticated understanding of hydraulic principles, even though they lacked the mathematical framework that would later be provided by people like Bernoulli and Euler in the 18th century. They couldn't write down the equations that governed fluid flow, but through careful observation and accumulated experience, they understood the practical realities well enough to design systems that worked. Marcus was fascinated by these practical principles. He conducted his own experiments, timing how long it took for water to flow through channels of different dimensions and different gradients, measuring the relationship between channel cross-section and flow rate. He became particularly interested in the problem of mineral deposits. All water contains dissolved minerals, and as water flows through an aqueduct, especially one made of stone or concrete, these minerals gradually precipitate out, building up on the walls and floor of the channel. Over time, years and decades, these deposits can significantly reduce the channel's capacity. Some of the older aqueducts had deposits more than 30 centimeters thick in places, reducing the effective cross-section by more than half. The standard solution was periodic cleaning, sending crews in to physically chip away the deposits, hard and tedious work. But Marcus wondered if there might be ways to minimize the build-up in the first place, perhaps by careful control of water velocity, or by using different lining materials, or by designing settling tanks that would remove more minerals before they entered the main channel. He wrote several reports on the subject, proposing various experiments and improvements. Some were implemented, others were deemed too expensive or too uncertain, but the reports caught the attention of senior officials, reinforcing Marcus's reputation as someone who didn't just follow established procedures but actively thought about how to improve them. In 71 AD, when Marcus was 24 years old, everything changed. The curator aquarum position became vacant, and the new emperor, Vespasian, appointed a man named Quintus Petilius Cerealis to the role. Cerealis was a military man, a successful general who had recently returned from Britannia, and he had no background in engineering or water management. But he was energetic and ambitious, and he immediately set about reorganizing the department. One of his first decisions was to create a new position, a deputy curator who would handle the technical aspects of the work while Cerealis himself focused on the administrative and political side. And for this position, he chose Marcus Vitruvius Aquilo. Marcus was stunned. He was only 24. There were engineers in the department with 2 or 3 times his experience, but Cerealis had reviewed the personnel records, read Marcus's reports, and talked to people who had worked with him. He wanted someone who was technically excellent, who understood the systems deeply, who could be trusted to identify real problems and solve them properly. Age wasn't the issue. Marcus accepted the position, though he felt the weight of it immediately. As deputy curator, he was now responsible for the entire aqueduct system of Rome. 9 major aqueducts, more than 400 kilometers of channels and pipes and arcades, delivering more than 1 million cubic meters of water per Dalton Y to a city of nearly 1 million people. The scope of it was almost overwhelming when you really thought about it. One of Marcus's first actions in his new role was to organize a systematic inspection schedule. Rather than waiting for problems to develop and then reacting to them, he wanted regular routine inspections of every part of every aqueduct, so that issues could be caught early when they were small and easy to fix, rather than late when they had become crises. He divided the entire system into sections and assigned teams to each section, with each team responsible for walking their section once per month and filing a report on its condition. This required expanding the workforce, hiring more inspectors and maintenance crews, which required money, which required convincing Cerealis, and through him the imperial treasury, that the investment was worthwhile. Marcus made his case with data. He showed that reactive maintenance, where you waited for failures and then fixed them, was actually more expensive in the long run than proactive maintenance, where you prevented failures through regular upkeep. He showed that major failures disrupted water supply, which affected public baths, fountains, and private users, which led to complaints and political problems. He showed that small repairs were cheap, while large repairs were expensive, and that catching problems early meant more small repairs and fewer large ones. It was a compelling argument, and Cerealis supported it. The funding was approved, the new inspectors were hired, and the systematic inspection program was implemented. Within a year, the difference was noticeable. The number of emergency repairs dropped. The average flow rates of the aqueducts increased as small leaks and blockages were caught and fixed. Water quality improved, and the cost of maintaining the system actually decreased, because they were no longer dealing with as many expensive crises. According to Dr. Catherine Rinn from the University of Oregon, who has made a detailed study of Rome's water infrastructure, this kind of systematic proactive maintenance was actually fairly unusual in the ancient world. Most infrastructure was maintained reactively, if it was maintained at all. The fact that Rome's aqueducts continued to function reliably for centuries was a direct result of the kind of careful, professional management that people like Marcus provided. It is easy to take functioning infrastructure for granted. The water flows when you turn on the tap. The lights come on when you flip the switch. The road is there when you need to drive somewhere. We don't think about it until it stops working, and then we're outraged. But keeping infrastructure functioning requires constant, ongoing effort. It requires inspection and maintenance and repair. It requires people who understand the systems and care about keeping them working. It requires investment of time and money, often with no visible result, because the whole point is to prevent problems that most people never know could have happened. Sound familiar? We're dealing with this right now today. Aging water systems with pipes that are 50, 70, 100 years old, leaking, breaking, contaminating the water supply. Bridges that are structurally deficient, roads full of potholes, electrical grids that can't handle modern demand. And part of the reason we're in this situation is because for decades we deferred maintenance. We didn't want to spend money on boring things like fixing pipes and repaving roads. We wanted new things, exciting things. And now we're paying the price in more expensive repairs, in disruptions, in occasional catastrophic failures. Marcus understood this. He understood that the unglamorous work of regular maintenance was actually the most important work he could do, and he fought for it politically and bureaucratically year after year. But Marcus's role wasn't only about maintenance. It was also about expansion, about planning for Rome's growing needs. And in 73 AD, he was given the opportunity to work on what would become his masterpiece. Emperor Vespasian, who was in the process of rebuilding Rome after the chaos of the civil wars and the Great Fire, wanted a new aqueduct. Rome's population was growing. The existing aqueducts, even running at full capacity, were barely meeting demand. Vespasian wanted a major new source of water, and he wanted it to be a monument to his reign, a grand public work that would benefit the city for generations and carry his name forward. He allocated a budget of 200 million sesterces for the project, an enormous sum, roughly equivalent to the cost of constructing the Colosseum, which was being built at the same time, and he put Cerealis in charge, which effectively meant he put Marcus in charge, since Marcus would be handling the actual engineering. This was it. This was the opportunity Marcus had been preparing for his entire career. A chance to design and build a major aqueduct from scratch with adequate funding and imperial support. It was exhilarating and terrifying in equal measure. The first step was to find a suitable water source. This wasn't simple. You needed a source with enough flow to make the project worthwhile. Thousands of cubic meters per Dalton Y. You needed water of good quality, clean and safe to drink. And you needed a source that was elevated enough above Rome that water could flow downhill all the way to the city. Marcus spent months on this initial survey phase, travelling throughout the countryside east and north of Rome, investigating potential springs and rivers, measuring their flow rates and elevations, testing their water quality, calculating possible routes. He was looking for a source at least 15 to 20 meters higher than Rome's highest point to ensure adequate pressure for distribution once the water reached the city. Eventually, he found what he was looking for, a group of springs in the Sabine Hills, about 48 kilometers east of Rome, at an elevation of approximately 318 meters above sea level. The springs produced a combined flow of about 5,500 cubic meters per H-hour, or roughly 132,000 cubic meters per Dalton Y, a very substantial addition to Rome's supply. The water was cold, clear, excellent quality, and the elevation was perfect, high enough to provide good pressure. Marcus returned to Rome and presented his findings to Cerealis and to Vespasian himself. He brought maps, calculations, samples of the water. He explained the route the aqueduct would take, the technical challenges they would face, the time and resources it would require. Vespasian, who, despite being emperor, was known for his practical, no-nonsense approach to governance, asked hard questions about cost and schedule. Marcus answered them honestly. This would be a major undertaking, requiring at least 4 years of intensive work and the labour of thousands of men. But when it was complete, it would provide enough water for approximately 500,000 people, effectively ensuring Rome's water supply for the foreseeable future. Vespasian approved the project in the summer of 73 AD, and Marcus began the detailed planning. According to Dr. Evan Haley from the University of Maryland, who has studied the political economy of Roman public works, projects of this scale involved complex negotiations between multiple stakeholders. The emperor provided overall approval and funding, but the actual work involved contracts with private firms for various tasks, coordination with local landowners along the route who would be affected, arrangements with the army for provision of skilled engineers and surveyors, and careful management of public expectations. A project like this was never purely technical. It was always also political, economic, and social. Marcus's first task was the detailed route survey. He knew the start point, the springs in the Sabine Hills. He knew the end point, Rome. Now he needed to determine the exact path the aqueduct would take between them, a path that would maintain a consistent downhill gradient, avoid obstacles as much as possible, and minimize construction difficulties and costs. This is where Roman surveying really showed its sophistication. With a team of surveyors and assistants, Marcus began at the springs and worked toward Rome, measuring elevations at regular intervals, mapping the terrain, calculating optimal routes. The primary tool for this work was the chorobate, that same instrument he had first seen Petronius use all those years ago in Veii. A chorobate was essentially a long wooden beam, typically about 6 meters long, with a narrow water trough cut into its top surface and vertical posts at each end. When the beam was perfectly level, the water in the trough would be the same height at both ends. By sighting along the water surface and adjusting the beam until it was level, then measuring the heights of the vertical posts above the ground, you could determine the relative elevation of 2 points. It was simple in concept, but remarkably accurate when used carefully, According to Professor Trevor Hodge, tests have shown that skilled Roman surveyors using a chorobate could achieve accuracy within a few centimetres over distances of several hundred metres. By leapfrogging the instrument forward, measuring from one station to the next, they could map elevations over long distances with cumulative errors of less than half a metre, sometimes less. For an aqueduct 48 kilometres long, dropping from 318 metres elevation to about 30 metres elevation at Rome, the overall gradient was about 0.6%, well within the acceptable range. But of course, the route wouldn't be straight. It would wind around hills, cross valleys, avoid rock formations that would be too difficult to tunnel through. In some places, the gradient would be steeper, in others more shallow. The art was in balancing these variations to maintain an overall gradient that kept water flowing steadily without excessive velocity. Marcus spent 6 months on the survey, 6 months of tramping through the countryside, taking measurements, making notes, revising routes when obstacles appeared, calculating and recalculating. He went through dozens of wax tablets filled with figures. He drew and redrew maps. He consulted with local residents about soil conditions and seasonal flooding. He investigated every aspect of the route with obsessive thoroughness, because he knew that mistakes made now in the planning phase would become expensive problems during construction. Think about that. 6 months of planning before a single spadeful of earth was moved. In our modern world of fast-paced development and just-in-time everything, we sometimes forget the value of thorough planning. We want to start building immediately, to see visible progress. But as any experienced engineer will tell you, time spent in careful planning is time well invested. It is much easier and cheaper to change a line on a map than to reroute a half-built tunnel. By the spring of 74 AD, Marcus had his route finalized. The aqueduct would run 48.7 kilometers from source to city. For about 32 kilometers, it would run underground through tunnels and covered trenches. For the remaining 16.7 kilometers as it approached Rome, it would run on arcades, those magnificent arch structures that allowed the channel to maintain its elevation while crossing lower ground. At its highest point, the arcade would be 32 meters above the ground, supported by arches stacked 2 and sometimes 3 levels high. The channel itself would be approximately 1.2 meters wide and 1.8 meters high, lined with waterproof opus signum mortar. With these dimensions and the planned gradient, Marcus calculated that the aqueduct would deliver approximately 4,690 cubic meters of water per HR, assuming the channel ran about 60% full, which was optimal. That worked out to about 112,500 cubic meters per Dalton Y, close to his original estimate. Now came the hard part, actually building it. For a project of this scale, Marcus needed a large workforce, not just common labourers, though he would need plenty of those, but also skilled workers of various types, stone masons, tunnel diggers, carpenters for building formwork and centering for the arches, lime burners for mortar production, smiths for maintaining tools, surveyors, engineers, foremen to supervise work gangs. According to modern estimates by scholars like Dr. Lynn Lancaster, a major aqueduct project like this would typically employ somewhere between 2,000 and 3,000 workers at peak construction. Some were direct employees paid wages from the project budget. Others were slaves, owned by contractors who bid for various portions of the work. Still, others were soldiers, assigned from the legions for the more technical tasks. The Romans often used soldiers for major construction projects because legionaries included many skilled tradesmen, and because military units already had the organizational structure to manage large-scale coordinated work. Marcus organized the project into several major work sections, each with its own team and supervisor. One section would work on the spring houses and collection system at the source. Another would excavate the underground sections. Another would build the arcades. Each section was further subdivided into smaller crews, each responsible for a specific task. Coordination was crucial. The underground sections had to be excavated on correct gradients and alignments so that they would connect properly. Materials had to be delivered to work sites when needed, which meant quarries had to produce stone, kilns had to produce lime, all on careful schedules. Workers had to be housed and fed, which required setting up temporary camps along the route. The sheer logistics of it were staggering. Think about managing 2,000 workers in an age before electronic communication, before motorized transport, before any kind of project management software. You are coordinating everything with messengers on horseback, with written orders, with personal inspections. You are doing all your calculations by hand. You are tracking all your resources and expenses with physical ledgers, and any mistake, any miscommunication, any error in planning could result in wasted time, wasted money, or worse, injury and death. Marcus approached it methodically. He set up a project headquarters in a small town along the route, about halfway between the source and Rome. He hired senior foremen for each major work section, experienced men who knew their trades and knew how to manage workers. He established regular reporting requirements, with each foreman required to submit weekly reports on progress, problems encountered, materials consumed, workers present. He made regular inspection tours, riding the length of the project to see work firsthand, to talk to the foreman, to check that quality standards were being maintained. And he kept meticulous records of everything, creating what we might now call a project archive, documenting every decision made, and why, every problem encountered, and how it was solved. According to Professor Rubben Taylor from the University of Texas at Austin, who has studied Roman architectural and engineering practice, this kind of systematic documentation was characteristic of major Roman projects. They understood the value of written records, both for current management and for future reference. Many of the technical manuals that survive from ancient Rome are based on this accumulated project documentation. Construction began in earnest in the summer of 74 AD and would continue for the next 3.5 years. Let me take you through some of what that actually involved, because the technical details are fascinating, and because they show just how sophisticated Roman engineering really was. Start with the underground sections. For sections where the aqueduct ran underground, there were two main approaches. If the terrain was relatively flat and the soil was stable, they would dig an open trench, build the channel in the bottom of it, then cover it over. But for sections running through hills, they would excavate tunnels. Tunnel excavation was slow, difficult, dangerous work. A typical tunnel for an aqueduct was about 2 meters high and 1 meter wide, just large enough for the water channel and for workers to move through for maintenance. The Romans typically excavated from multiple points simultaneously to speed the work. They would sink vertical shafts down from the surface at intervals of 40 to 60 meters, then excavate horizontally in both directions from each shaft, meeting in the middle. This required extremely accurate surveying. You had to ensure that the horizontal tunnels from adjacent shafts were perfectly aligned, or they wouldn't meet, and you had to maintain the correct gradient throughout. Even a small error compounded over distance could result in tunnels that were misaligned or had incorrect slopes. How did they maintain alignment? Very carefully. They would drop plumb lines down the vertical shafts to establish vertical reference points. They would use lamps placed at specific locations to provide sighting lines for horizontal alignment, and they would constantly measure distances and elevations, checking against the survey data. Even with all these precautions, tunnels sometimes didn't meet perfectly. When that happened, they had to make adjustments, usually by widening one tunnel to connect with the other. You can actually see evidence of this in surviving Roman tunnel work, places where the tunnel jogs slightly to connect with the next section. The excavation itself was done by hand, with picks and chisels and wedges. If the rock was relatively soft, like tufa or limestone, the work went reasonably quickly, maybe 2 to 3 meters of tunnel per Dalton Wiper crew. If the rock was harder, progress slowed to a crawl, sometimes only a few centimeters per Dalton Y. For very hard rock, they sometimes used fire setting, heating the rock with fires and then cooling it rapidly with water, causing it to crack. But this was time-consuming and dangerous. According to Dr. Marie Jackson from the University of Utah, who has studied Roman concrete and mortar extensively, the Romans eventually developed techniques for lining tunnels with a waterproof coating of opus signinum, a mortar made from lime, volcanic ash called pozzolana, and crushed pottery. This mortar had remarkable properties. It set hard even underwater, it was essentially waterproof, and it was durable, lasting for centuries. The recipe varied somewhat, but a typical mix might be 1 part lime, 2 parts pozzolana, and 3 parts crushed pottery, mixed with water to a thick paste. This would be applied to the tunnel walls and floor in a layer several centimeters thick, then smoothed to create a uniform channel for the water. As the underground sections were being excavated, other crews were working on the arcade sections. This was some of the most impressive work, and when people today think of Roman aqueducts, this is usually what they picture: the tall stone arches marching across the landscape. Building arcades required different skills than tunneling. You were working with cut stone, building arches and piers often to considerable heights. The process started with foundations. Deep trenches were dug down to bedrock or solid soil, then filled with layers of stone and mortar to create stable bases for the piers. The piers themselves were massive, typically 2 to 3 meters square at the base, built of cut stone blocks set in mortar. As the piers rose, they often tapered slightly, becoming narrower at the top, both to save material and for aesthetic reasons. Once the piers were built to the required height, the arches could be constructed. This required wooden formwork called centering. Carpenters would build a temporary wooden arch of the correct shape, supported on the tops of 2 piers. Then masons would lay stone blocks around this wooden frame, starting at both ends and working toward the middle, with each block cut to the correct wedge shape. The final block, placed at the top center of the arch, was called the keystone. Once it was in place and the mortar had set, the arch was self-supporting, carrying its weight through compression down into the piers. The wooden centering could then be removed and reused for the next arch. For a single-level arcade, this was relatively straightforward, if labor-intensive, but Marcus's aqueduct, in some sections, required 2 or even 3 levels of arches stacked on top of each other to achieve the necessary height. This made the work much more complex and dangerous. Workers were laboring 30 meters above the ground, on wooden scaffolding, handling heavy stone blocks, working with mortar. Falls were common. Scaffolding sometimes collapsed. During the 3.5 years of construction, Marcus lost 23 men to accidents on the arcade sections. 23 men who fell, or were struck by falling materials, or were crushed when scaffolding failed. Each death was investigated. Marcus wanted to understand what had gone wrong, whether anything could have been done to prevent it. Sometimes the answer was yes. A safety procedure was added. Scaffolding requirements were strengthened. Sometimes the answer was no. It was just bad luck, a moment's inattention, the inherent risk of the work. What really gets to me thinking about this is how these men are forgotten. We have this magnificent infrastructure, these beautiful arcades that still stand today, that we admire as tourists, but we don't think about the men who built them, who died building them. We don't know their names, most of them. We don't know their families, their dreams, what they might have accomplished if they'd lived. They're just gone, their sacrifice unmarked, except in the stones they laid. Marcus knew their names, Marcus remembered. Gaius Valerius, who fell from scaffolding in the first year. Publius Aelius, crushed when a crane failed. Titus Flavius, Lucius Petronius, Marcus Antonius. He attended their funerals when he could. He arranged for their families to receive compensation, not required by law but something he insisted on, and he carried their weight. By the winter of 76 AD, halfway through the construction schedule, the project was actually slightly ahead of plan. The underground sections were nearly complete. About half the arcade sections were finished. The collection system at the springs was done and working, already channeling water into the completed sections of the aqueduct, which allowed Marcus to test them for leaks and flow characteristics. Everything looked good, and then, in early spring of 77 AD, disaster struck. A section of tunnel, about 200 meters long, collapsed. It happened at night, which was fortunate in that no workers were in the tunnel at the time, but it was still catastrophic for the project. 200 meters of completed tunnel just gone, caved in, filled with earth and rock. Marcus got the news by messenger at dawn and rode immediately to the site. What he found was sobering. The tunnel had been excavated through what they thought was stable soil, a mixture of clay and gravel, but there must have been an underground water source they hadn't detected during surveying. The water had slowly saturated the soil, weakening it, until finally the weight of the earth above was too much and the tunnel ceiling gave way. Now Marcus faced a choice. They could try to excavate the collapsed section again, shoring it up more carefully this time, but if there was indeed an underground water source, they might just have the same problem again. Or they could reroute this section, either finding a way to tunnel through more stable ground, or bringing the aqueduct above ground here. Rerouting meant redesigning this section, which meant resurveying, recalculating gradients, possibly building an arcade section that hadn't been in the original plan. It meant delay and additional cost, but it was probably the safer choice. Marcus made the decision to reroute. He brought in his surveying team, and they spent 2 weeks mapping the area, investigating the geology, looking for alternatives. Eventually they determined that by shifting the route about 300 meters to the north, they could avoid the unstable area, running through rock that could be tunneled safely. It would require excavating a new tunnel section, about 350 meters long through harder rock than the original route, which would be slow work, and it would require building a short arcade section, about 60 meters, to maintain the elevation where the new tunnel emerged. It would add about 3 months to the schedule and about 12,000 sesterces to the budget, but it would work and it would be stable. Cerealis, when Marcus reported the situation and his proposed solution, was not happy about the delay or the cost overrun, but he recognized that Marcus was making the right choice. "Fix it properly," he said. "I'll handle the political side." The political side meant explaining to Emperor Vespasian why his prestigious project was delayed and over budget. Vespasian, to his credit, understood that large construction projects rarely went exactly according to plan. He approved the additional funding and accepted the revised schedule. Work continued. The new tunnel section was excavated over the summer and fall of 77 AD. It was hard going, harder than Marcus had anticipated, because the rock turned out to be even more difficult than they'd expected. The work slowed to about 1 meter per Dalton year, sometimes less, but it was stable. There would be no collapses here, and meanwhile, work on other sections continued. By the end of 77 AD, all the arcade sections were complete. By early 78 AD, all the underground sections were complete, including the rerouted section. The channel had been lined throughout with opus signinum. Settling tanks had been built at the source and at key points along the route. Distribution infrastructure in Rome had been prepared to receive the new water. Everything was ready. Now came the moment of truth. The first water test. This was always a tense moment with a new aqueduct. You could do all the calculations, all the surveys, all the careful construction, but you never really knew if it would work until you actually tried to run water through it. Would the gradient be right? Would there be leaks? Would there be flow problems? Marcus chose a day in late March of 78 AD for the test. He positioned observers at key points all along the aqueduct's length, men stationed at each settling tank, at the beginning and end of each major section, at the terminus in Rome. Each observer had instructions to watch for water arrival and to check for any problems, leaks, overflow, anything unexpected. Then, at the source, Marcus personally opened the gates that had been holding back the spring water from entering the aqueduct channel. Water began to flow. Marcus watched it enter the channel, watched it begin its journey toward Rome, 48.7 kilometers away, at a flow velocity of about 0.7 meters per second, which is what he'd calculated for. It would take about 19 hours for the first water to reach Rome. Marcus rode back to the city, stopping at observation points along the way. At each stop, the report was the same. Water had arrived, flowing smoothly, no problems observed. By the next morning, Marcus was at the terminus in Rome, watching the distribution basin. If everything had worked, water should start arriving soon. A small crowd had gathered, word having spread that the new aqueduct was being tested. Cerealis was there. Several senators who had supported the project, engineers from Marcus's staff, workers who had built the structure. They waited. The sun climbed higher. Noon approached. And then someone shouted, "Water, I see it." And indeed, there it was, water flowing into the basin, clear and cold and pure. The first water from the new aqueduct flowing into Rome. The crowd cheered. People embraced each other. Marcus found himself being congratulated, slapped on the back, praised. He smiled and accepted the congratulations, but inside he was just relieved. It worked. After 4 years of planning and construction, after the setbacks and the accidents and the deaths and the anxiety, it worked. Over the next several days, as the aqueduct reached full flow, Marcus and his team made careful measurements. The flow rate was 4,710 cubic meters per H-hour, very close to the design target of 4,690. The water quality was excellent. The distribution system was handling the new flow without problems. By every measure, the project was a success. Emperor Vespasian formally dedicated the new aqueduct in a public ceremony in April of 78 AD. In his honor, it was named the Aqua Augusta Vespasiana. Vespasian himself gave a speech praising the work and highlighting how the new water supply would benefit Rome for generations to come. He mentioned Cerealis by name, crediting him with overseeing the project. He did not mention Marcus, but Marcus didn't expect him to and didn't mind. He knew what he'd accomplished. His colleagues knew. That was enough. Think about that for a moment. 4 years of his life poured into this project. The stress, the responsibility, the difficult decisions, the grief over the men who died, and at the formal dedication he is not even mentioned. How would that make you feel? Would you be bitter, resentful? Marcus wasn't. He understood how the world worked. The credit went to the powerful, to the emperor and the high officials. The actual builders, the engineers and workers, they were expected to find satisfaction in the work itself. And Marcus did find satisfaction in it. Every time he saw water flowing from a fountain, supplied by his aqueduct, every time he walked past the arcades and saw them standing strong and beautiful, he felt a deep sense of pride. He had built something real, something lasting, something that mattered. That was his reward. Over the next several years, Marcus continued his work as deputy curator. Rome now had 10 major aqueducts, the 9 original ones plus the new Aqua Augusta Vespasiana. Together, they delivered about 1.13 million cubic meters of water per Dalton Ui, enough to meet the city's needs with some margin for growth. But water infrastructure isn't something you can build and then forget. It requires constant maintenance, constant vigilance. The systematic inspection program Marcus had established continued, catching and fixing small problems before they became large ones. And Marcus also continued to think about the long term, about what would be needed 10, 20, 50 years in the future. He knew that Rome's population would likely continue to grow. He knew that the existing aqueducts would age, that their capacity would gradually decline as deposits built up and materials deteriorated. He knew that climate could vary, that the springs feeding the aqueducts could have years of high flow and years of low flow. All of this meant that Rome needed to think about water security, about having enough capacity to meet needs even in difficult years, about planning for future expansion. Marcus wrote several long reports on these topics proposing various strategies. Some were implemented during his tenure, others were filed away to be reconsidered by future administrations. In 79 AD, Vespasian died and was succeeded by his son Titus. Titus reappointed Cerealis as curator aquarum, and Marcus continued as deputy. But Titus's reign was brief. He died in 81 AD and was succeeded by his brother Domitian. Domitian made some changes to the administration, and Cerealis was replaced as curator. Marcus was offered the option to stay on as deputy under the new curator, but he declined. He was 34 years old. He had been working on aqueducts for 21 years since he was 13. He was tired. The years of stress, the constant responsibility, the physical toll of the work, it had worn on him. He wanted a different pace of life. He resigned from the office of the curator aquarum and took a position as a consulting engineer, working on a contract basis for various cities and private clients who needed water systems designed or fixed. It was less prestigious than his previous role, and it paid less, but it also gave him more control over his time and his work. He could choose which projects to take, could spend more time on design and less on administration. Over the next decade, Marcus worked on aqueducts and water systems for a dozen different cities across Italy and the provinces. He designed a new aqueduct for Ostia, Rome's port city. He repaired aging systems in Naples and Pompeii. He advised the city of Lyon in Gaul on expanding their water supply. He consulted on systems in Spain and North Africa. He became known as one of the empire's leading experts on water engineering, someone worth paying premium fees to secure his services. He also wrote. Drawing on his decades of experience, he began to compile a technical manual on aqueduct design and construction, documenting the principles and practices that he had learned and developed. This wasn't entirely original work. He drew heavily on the writings of Vitruvius Pollio and other earlier engineers, but he updated their work with his own insights, added details on newer techniques, included case studies from projects he had worked on. According to Dr. Catherine Rinn, technical manuals like this played a crucial role in preserving and transmitting engineering knowledge in the Roman world. Unlike some other ancient societies where technical knowledge was closely guarded as trade secrets, the Romans had a tradition of writing down and sharing engineering knowledge, allowing each generation to build on the work of previous ones. In 89 AD, when Marcus was 42, he married. Her name was Julia Procula, the daughter of a merchant, a woman of about 30, intelligent and capable. They had met through mutual friends in Rome, and Marcus, who had been so focused on his work for so long that he'd never seriously thought about marriage, found himself genuinely charmed by her. They married in a simple ceremony and set up a household in a comfortable house on the Esquiline Hill in Rome. Over the next several years they had 3 children, a daughter, Claudia, born in 90 AD, a son, Marcus Jr., born in 92 AD, and another daughter, Livia, born in 94 AD. Fatherhood changed Marcus in subtle ways. It gave him a new perspective on the long-term nature of his work. When he looked at his children, he thought about the world they would inherit. He thought about the infrastructure that would support their lives, the water they would drink, the buildings they would use. It reinforced his belief in the importance of building well, building to last, thinking about the future. His son, young Marcus, showed an early interest in his father's work. From the time he could walk, he was fascinated by the aqueducts, by the flow of water, by the technical drawings his father kept in his study. Marcus Sr. would take the boy on walks to observe the arcades, to visit distribution basins, to watch the fountains. He would explain how it all worked, in simple terms at first, then in increasing detail as the boy got older and more capable of understanding. By the time young Marcus was 10, in 102 AD, it was clear that he wanted to follow in his father's footsteps. Marcus Sr. arranged for his son to begin a formal education in mathematics and engineering, the same path he himself had followed. He introduced the boy to colleagues, arranged visits to construction sites, began teaching him surveying and calculation. It gave Marcus Sr. deep satisfaction to see his knowledge being passed to the next generation, to his own son. But time was passing. Marcus Sr. was in his 50s now, and while he was still healthy and active, he could feel the years accumulating. The work was harder than it used to be. Climbing down into tunnels, walking long distances to inspect aqueducts, working in cold water, it took more of a toll than it once had. He began to take fewer projects, to be more selective about the work he accepted. In 106 AD, when Marcus was 59, he received a request from the office of the curator Aquarum. Would he be willing to undertake one more major project for Rome? There were problems with the Aqua Claudia, one of the great aqueducts now more than 60 years old. It needed major repairs and upgrades. It was exactly the kind of complex, challenging work that Marcus had spent his career preparing for, but it would be demanding. It would require several years of intensive effort. He discussed it with Julia. He was almost 60. He could decline, could continue his semi-retirement, could focus on training his son and enjoying his remaining years, or he could take on one more great work, could use everything he had learned over a lifetime to restore a critical piece of Rome's infrastructure. He decided to accept. This would be his final project, his last great work, and he would bring his son, now 14, to work with him, to learn, to see what the work really involved. The Aqua Claudia was one of Rome's engineering marvels, built during the reign of Emperor Claudius and completed in 52 AD. It ran about 69 kilometers from its sources to Rome, and at its peak capacity it delivered about 190,000 cubic meters of water per Dalton Nye. But 69 kilometers of infrastructure, after more than half a century of continuous use, had developed numerous problems. There were leaks. There were sections where deposits had reduced flow capacity. There were structural issues with some of the arcades. There were contamination sources that needed to be found and eliminated. It was, in many ways, similar to the very first major project Marcus had worked on, the repair of the Aqua Marcia, more than 40 years earlier. But now he was the senior engineer, not the junior assistant. He brought to the work 4 decades of accumulated knowledge and experience, and he brought his son to teach him the same lessons he had learned from Vianto all those years ago. They spent months walking the aqueduct, inspecting every section, documenting every problem. Young Marcus learned what his father already knew, that most of engineering wasn't dramatic or exciting. It was methodical, systematic, careful observation and documentation. It was attention to detail. It was patience. They found more than 60 issues requiring attention. Some were simple, some were complex. Marcus Sr. designed solutions for each, drawing on his experience with similar problems. He organized a workforce, developed a schedule, coordinated with contractors, and slowly, systematically, over 2.5 years, the Aqua Claudia was restored. By the time the project was completed in 109 AD, the Claudia was flowing better than it had in decades. The flow rate was back up to design capacity. The water was clean and pure. The structure was sound. It was good work, and Marcus was proud of it. But he was also exhausted. He was 62 now, and he felt every one of those years. The work had taken more out of him than he wanted to admit. When the Claudia project was finished, Marcus formally retired. No more projects, no more consultations. He would spend his remaining time with his family, writing, teaching his son, enjoying the city he had helped to sustain. He had earned the rest. Marcus Vitruvius Aquilo died in the summer of 114 AD, at the age of 67. He died at home, surrounded by his family, which was as much as anyone in the ancient world could hope for. He was buried in a modest tomb outside the city walls, with a simple inscription, Marcus Vitruvius Aquilo, engineer. He brought water to Rome. His son, Marcus Jr., was 22 at the time of his father's death, already working as a junior engineer in the office of the curator, Aquarum. He would go on to have his own distinguished career, continuing his father's work, maintaining and expanding Rome's water infrastructure. The knowledge passed on, generation to generation, as it had to if the systems were to continue functioning. According to Dr. Walter Scheidel, this multi-generational continuity was one of the key factors in Rome's success at maintaining complex infrastructure over centuries. Engineering knowledge wasn't just written in books. It was embedded in families and professional lineages passed from father to son, from master to apprentice, accumulating and refining over time. Marcus himself, in his lifetime, saw the effects of his work on 1 million people. The water he brought to Rome, the systems he maintained and repaired, they supported life on an unprecedented scale. People drank the water he delivered. They bathed in it. They used it to cook, to clean, to water their gardens, to run their businesses. Most of them never knew his name. Most of them never thought about where the water came from or how it got there. It just flowed from the fountains, reliable and clean, day after day, year after year. That invisibility, that thanklessness was built into the job. But think about what it means. Marcus spent 54 years of his life, from age 13 when he first apprenticed to age 67 when he died, working on water infrastructure. That is 54 years of effort, of problem solving, of dealing with technical challenges and political complications and human tragedies. 54 years of choosing to do work that was essential but largely unrecognized. Why? Why dedicate your life to something like that? I think it is because Marcus understood something fundamental. He understood that civilization, real civilization where large numbers of people can live together in relative health and safety and prosperity, that civilization depends on infrastructure. It depends on systems that work day in and day out, systems that deliver clean water and remove waste and provide transportation and enable communication. These systems are the foundation that everything else is built on. Without them, cities can't exist, culture can't flourish, progress can't happen, and someone has to build these systems, someone has to maintain them, someone has to care about the details, about the gradients and the flow rates and the material properties and the long-term sustainability. Someone has to do the unglamorous work of keeping things functioning. Marcus was someone who did that work, and he wasn't alone. There were thousands like him, engineers and technicians and workers, throughout the Roman Empire and throughout history, people who built the infrastructure that made civilization possible. Most of their names are forgotten, but their work remains. Think about that in terms of our modern world. Right now, at this very moment, there are people maintaining the infrastructure you depend on. Engineers who design and repair water systems, electrical grids, transportation networks. Workers who fix the pipes when they break, who replace worn components, who keep everything running. You probably don't know their names. You probably don't think about them unless something goes wrong. But they're there, doing essential work, work that keeps our civilization functioning. Sound familiar? It should, because we're still facing the same fundamental challenges that Marcus faced. How do we build infrastructure that will last? How do we maintain aging systems? How do we plan for future needs? How do we balance short-term costs against long-term benefits? How do we ensure that essential services remain reliable? The technology has changed. We have pumps and computers and advanced materials that the Romans never dreamed of. But the underlying questions, the fundamental challenges of creating and maintaining the systems that support modern life, those remain the same. And the need for people who will dedicate themselves to that work, who will care about the details, who will think long-term, who will do the patient, unglamorous work of keeping things functioning, that need remains as well. According to Professor Norman Smith, studying historical infrastructure systems like Roman aqueducts isn't just about understanding the past. It is about learning lessons that remain relevant today. The Romans succeeded at water management because they combined technical knowledge with long-term thinking and sustained maintenance. When any of those elements was missing, systems failed. We see the same pattern today. Modern infrastructure projects fail not usually because of lack of technical knowledge, but because of inadequate planning, insufficient maintenance, or short-term thinking that sacrifices long-term sustainability. As we come to the end of this journey through Marcus's life, I want you to think about what his story means. On one level, it is a story about ancient engineering, about how the Romans built those magnificent aqueducts that we still admire today. But on a deeper level, it is a story about dedication, about finding meaning in work that serves others, about the satisfaction of building something that lasts, something that matters. Marcus lived a good life, not an easy life. He faced challenges, setbacks, tragedies. He bore heavy responsibilities. He made difficult decisions. He grieved for men who died under his supervision. He dealt with the frustrations of politics and bureaucracy. But he also experienced the deep satisfaction of solving complex problems. He built things that endured, that served millions of people over generations. He passed on his knowledge to his son and to others who came after him. He made a difference in the world, a real, tangible, lasting difference. At the end, when he was dying, surrounded by his family, do you think he had regrets? I don't think so. I think he could look back on his life and know that it had meant something, that he had used his talents well, that he had contributed something valuable. Not everyone can say that. Not everyone gets to do work that matters in such a clear and concrete way. How many of us, at the end of our lives, will be able to point to something and say, I built that. It is still there. It is still serving people. I made that happen. That is a privilege, really. A privilege that Marcus earned through decades of dedicated work. Now, as you lie there, getting comfortable preparing for sleep, I want you to think about the invisible infrastructure in your own life. Think about the water that flows from your tap. Someone designed that system. Someone built it. Someone maintains it. You probably don't know who. Think about the electricity that powers your lights, the roads you drive on, the internet you use, all of it. All the systems you depend on, they exist because someone built them and someone maintains them. People you've never met, people whose names you'll never know, people who do essential work that mostly goes unrecognized. Maybe tomorrow, when you turn on your tap and water flows, you'll think of Marcus. You'll think of all the engineers and workers, ancient and modern, who make it possible for you to have clean water at the turn of a handle. Maybe you'll have a moment of gratitude for the invisible infrastructure that supports your life. And maybe if you are someone who builds or maintains or operates systems that others depend on, maybe you'll feel a sense of connection to Marcus and to all the people throughout history who have done that same essential work. Maybe you'll feel proud of your contribution, even if it goes unrecognized, because you'll know that it matters. The work matters. Infrastructure matters. Maintaining the systems that support civilization matters. It is not glamorous. It is often frustrating, but it is important, perhaps more important than we usually realize. Sweet dreams, my friends. Tonight, as you drift off to sleep, remember Marcus Vitruvius Aquilo, the engineer who brought water to Rome. Remember the 48 kilometers of aqueduct he designed and built. Remember the careful surveys, the precise calculations, the years of construction, the men who died building it, the moment when water first flowed. Remember that this wasn't just ancient history. This was real. This happened. Real people did this work, faced these challenges, made these sacrifices, and their work echoes down through time to us. The principles they discovered, the techniques they developed, the infrastructure they built, some of it is still standing, still functional, 2,000 years later. Think about that as you fall asleep. Think about building things that last. Think about the long arc of time and your place in it. Think about the work you do and the difference it makes, even if that difference isn't always visible, even if it isn't always recognized. You are part of a long chain of humans trying to build something better, something that will last, something that will serve others. Marcus was part of that chain. We're all part of that chain. Sleep well. Dream of aqueducts and flowing water, of stone arches standing strong against the sky, of the quiet satisfaction of work done well. Dream of building something that matters. And when you wake, carry that forward. Carry forward the lesson of Marcus's life, that dedication to essential work, even invisible work, is a life well lived, that contributing to the infrastructure that supports others, that thinking long term, that building to last, these are worthy ways to spend your time on this earth. The water still flows, the work continues, and in our own ways, with our own tools, facing our own challenges, we carry on the work that people like Marcus began centuries ago. Rest now. Let these thoughts settle in your mind. Let the story of Marcus's life, his challenges and triumphs, his dedication and skill, Let it be a companion for your dreams tonight. You are part of something larger than yourself, we all are, and that is a beautiful thing to remember as you drift off to sleep. Sweet dreams, friends, sweet dreams tonight. As you drift off to sleep, remember the invisible heroes who keep our world running. Remember Marcus. Remember the water. Remember that behind every system you depend on, there are people who care, who work, who dedicate their lives to keeping things functioning. And be grateful. Be grateful for the infrastructure you often take for granted. Be grateful for the work of countless unknown people who make your life possible. And if you do work like that yourself, building or maintaining or operating the systems that others depend on, be proud. Be proud of your contribution. It matters more than you know. Good night. But let me take you back now, back to those early years, because there is so much more to tell about how Marcus became the engineer he was. Let me take you deeper into his apprenticeship, into those formative years when he was learning not just the technical skills, but the way of thinking that would define his entire career. Because the truth is, those years from age 13 to 18 were when Marcus's character was forged, when he developed the habits of mind and the practical knowledge that would serve him throughout his life. When Marcus first arrived at the office of the curator Aquarum in November of 59 AD, just after his 13th birthday, he was terrified. Imagine it for a moment. You are a boy from a small town, the son of a stonemason, and suddenly you are in Rome, the greatest city in the world, surrounded by people who seem impossibly sophisticated and knowledgeable. The other apprentices, Gaius and Titus and young Decimus, they had been there for months already. They knew the routines, knew their way around, knew which of the senior engineers were patient and which were quick to anger. Marcus knew nothing. That first night, lying in the small room he shared with the 3 other boys, Marcus barely slept. The sounds of the city were so different from what he was used to. In Veii, nights were quiet except for the occasional dog barking or the watchman calling the hours. Here in Rome, the city never truly slept. There were carts rumbling through the streets, goods being delivered to markets before dawn. There were voices, laughter, sometimes arguments. There was the constant background hum of a million people living in close proximity. The room itself was spare but adequate. 4 narrow beds, one along each wall, a single oil lamp on a table in the centre, pegs on the walls for hanging their few possessions, a chest at the foot of each bed for storing clothes and personal items. It was clean and dry, which was more than many people in Rome could say about their accommodations. But to Marcus, used to his father's modest but comfortable house in Veii, it felt cramped and foreign. Gaius, who slept in the bed across from Marcus, noticed the new boy's restlessness. First night, he asked quietly, his voice cutting through the darkness. "Yes," Marcus admitted. "It is different here. You'll get used to it," Gaius said. "Took me a few weeks, but you adjust. The work is hard, but it is good. Priscus is tough, but he is fair. And if you are willing to learn, really learn, they'll teach you things that most people never get to know, things that matter." "I want to learn," Marcus said. "I really do." "Good," Gaius replied. "Then you'll be fine. Now get some sleep. I wake us at dawn, and the first week is always the hardest." The routine Marcus fell into over the following weeks was rigorous and unvarying. The day began at dawn, when a slave would come through the building, ringing a bell, rousing the apprentices and the junior engineers who also lived on site. Marcus and the other boys would wash quickly in the communal basin, cold water that made you gasp even in relatively mild weather. They would dress in their work tunics, simple undyed wool, practical and durable. Then they would go down to the common room for the morning meal. Breakfast was basic but filling. Bread, sometimes fresh, more often a day old. Cheese, olives, occasionally some dried fruit and watered wine or posca, that vinegar-watered drink that was a staple for working people. The food was provided as part of their apprenticeship, which meant Marcus didn't have to pay for it, a significant benefit since he received no salary during these first years. After breakfast, the apprentices would gather in the main workroom where Priscus held his morning lessons. This was when they studied the theoretical foundations of their craft. Mathematics first and foremost. Priscus was a firm believer that you couldn't be a good engineer without a solid grounding in mathematics. Numbers don't lie, he would say, over and over again like a mantra. Stone can deceive you, wood can deceive you, even your own eyes can deceive you. But if you calculate correctly, if you measure accurately, if you understand the mathematics, the numbers will tell you the truth. They started with basic arithmetic, which Marcus already knew from his schooling in Viand. Addition, subtraction, multiplication, division. But Priscus pushed them further. He taught them to work with fractions, with ratios, with proportions. He taught them the geometry of circles and triangles and rectangles. He taught them how to calculate areas and volumes, how to work out the capacity of a water channel based on its dimensions, how to determine the amount of material needed for a given construction project. According to Professor Serafina Cuomo from Durham University, who has studied Roman mathematics extensively, Roman engineers had developed practical mathematical techniques that were quite sophisticated, even though they lacked the symbolic algebra that would be developed centuries later. They worked problems using written descriptions and geometric diagrams, and they used tables of standard calculations that could be referenced for common situations. It was a different approach from modern mathematics, but it was effective for engineering purposes. Marcus discovered that he had a natural aptitude for this kind of thinking. He enjoyed the puzzle-solving aspect of mathematics, the way a complex problem could be broken down into simpler parts, each part solved separately, then assembled into a complete solution. He worked through problems carefully, showing all his steps, checking his work. Priscus noticed and began giving Marcus extra problems to work on, more challenging ones, pushing the boy to extend his abilities. But mathematics was only part of the morning lessons. They also studied materials. Priscus would bring in samples of different types of stone, tufa, limestone, marble, and he would explain the properties of each. Tufa was soft and easy to cut, good for ordinary construction where you needed a lot of material cheaply, but it wasn't very durable and would erode over time if exposed to flowing water. Limestone was harder, more durable, better for structures that needed to last. Travertine was harder still, and beautiful, often used for prestigious projects. Marble was the hardest and most expensive, reserved for the most important structures. Each stone had its place, its proper use. Part of engineering was knowing which material to specify for which application. They learned about mortar, about how lime mortar was made by heating limestone in kilns to produce quicklime, then mixing the quicklime with sand and mortar. They learned about the special waterproof mortar called opus signinum, made by adding crushed pottery to the lime mixture. The pottery fragments, Priscus explained, contained silicates that reacted with the lime to create a cement that could set even under water and was resistant to water penetration. Modern analysis has confirmed Priscus's understanding. According to Dr. Marie Jackson from the University of Utah, the Roman waterproof concrete was indeed remarkably sophisticated, using pozzolanic materials that created a durable, long-lasting cement. Some Roman concrete structures have proven more durable than modern concrete, lasting 2,000 years with minimal deterioration. They studied wood, learning to recognize different species and understand their properties. Oak was strong and durable, good for structural applications. Pine was lighter and easier to work, good for scaffolding and temporary structures. They learned about iron and bronze, about how iron tools were forged and tempered, about the uses of bronze in making measuring instruments and fittings. Think about this for a moment. These boys, 13, 14, 15 years old, were receiving an education in materials science, in mathematics, in engineering principles. It wasn't an abstract academic education. It was intensely practical, focused on the knowledge they would need to actually design and build things. But it required them to really understand the underlying principles, not just memorize procedures after the morning lessons, which typically lasted 3 to 4 hours. The apprentices would have a brief midday meal, bread and cheese again, perhaps some vegetables if they were in season, and then they would head out into the field for the afternoon practical work. This is when they truly learned their craft. Priscus would take them to visit the various aqueducts, walking long sections of the channels, teaching them to observe, to notice the subtle signs that indicated how well a system was functioning, or whether problems were developing. "Look at the water flow," Priscus would say, pointing into a channel. "See how it moves smoothly, evenly. That is good. That means the gradient is right. The channel is clear. But if you see turbulence, if you see the water churning and splashing, that could mean several things. Maybe there is an obstruction. Maybe the gradient is too steep in that section. Maybe there is a crack letting air in. You have to investigate, figure out what is causing it." He taught them to listen as well as look. The sound of water flowing in a channel had a characteristic tone, a steady rushing sound. Changes in that sound could indicate problems. A gurgling sound might mean air pockets. A change in pitch might indicate a change in flow rate. "Your ears are instruments," Priscus would tell them. "Learn to use them." They learned to recognize signs of leakage. A patch of unusually green vegetation near an underground channel might indicate water seeping out. A damp spot on an arcade pier might indicate a crack in the channel above. Mineral deposits on the outside of a channel wall meant water was penetrating through and evaporating, leaving the minerals behind. They learned to use the surveying instruments, though at first they only watched while more experienced engineers did the actual work. Marcus was fascinated by the corobot, that elegantly simple device for establishing level. It was just a wooden beam with a water trough, but in skilled hands it could measure elevations with remarkable precision. He watched how the surveyors would set it up carefully, making sure it was stable, waiting for the water in the trough to settle completely before taking a reading. He saw how they would take multiple measurements, averaging them to reduce error. Later, as they gained experience, the apprentices were allowed to practice with the instruments themselves under supervision. Marcus's first time using the corobate, he was nervous, afraid he would make a mistake. But Priscus was patient. "Take your time," he said. "There is no rush. Accuracy matters more than speed. Set it up properly. Wait for the water to settle. Take your reading. Check it. Take another reading. Compare them. Only when you are confident that you have it right should you record the measurement." Marcus followed the instructions carefully, and to his relief his measurements matched those taken by the more experienced surveyor. It was a small success, but it gave him confidence. He could do this work. He could learn it. They learned maintenance procedures by actually performing them. When a section of channel needed cleaning, removing accumulated sediment and mineral deposits, the apprentices would do the work under supervision. It was hard, physical labor. You would climb down into the channel, often through a narrow vertical shaft, descending on a wooden ladder in the darkness. At the bottom, you would wade through the flowing water, which was usually cold, sometimes painfully so. Then you would chip away at the deposits on the channel walls and floor using iron chisels and scrapers, filling baskets with the debris, hauling the baskets back up to the surface. It was exhausting, dirty, uncomfortable work. Your clothes would be soaked. Your hands would get raw from gripping the tools and hauling the baskets. Your back would ache from being bent over in the confined space. But it was necessary work, and doing it themselves gave the apprentices a visceral understanding of what aqueduct maintenance actually involved. They learned respect for the crews who did this work day in and day out. According to Dr. Philip Kay, who studied Roman labor practices, this kind of hands-on training was typical for technical apprenticeships. The apprentices weren't just learning theory, they were learning by doing, working alongside experienced craftsmen, gradually taking on more responsibility as their skills developed. It was an effective educational model, one that has been used in various forms throughout human history. In the evenings, after returning from the fieldwork, the apprentices would have their main meal of the day. This was usually more substantial than breakfast and the midday snack. There would be a grain dish, often a thick porridge made from barley or wheat. There might be vegetables, onions, cabbage, turnips, whatever was in season and cheap. Occasionally there would be meat, though not often, usually some pork or chicken, more commonly on festival days than as part of the regular routine. After dinner, the apprentices had some free time before bed. Some of them would use this time to socialize, playing games, talking, exploring the city. But Marcus, especially in those first months, usually spent his evenings studying. He would review the day's lessons, work through practice problems, read from the technical texts that were available in the office library. There was a copy of Vitruvius Pollio's De Architectura, the famous 10-volume treatise on architecture and engineering. Marcus read it carefully, multiple times, absorbing the principles the master architect had laid out. There were also various reports and documents from previous engineering projects, describing problems encountered and solutions implemented. Marcus found these case studies invaluable. They showed him that even experienced engineers faced difficulties, made mistakes, had to revise their plans. It was reassuring in a way. Perfection wasn't the expectation. Careful work and willingness to learn from errors, that was what mattered. Gaius would sometimes tease him about his studiousness. "You'll wear out your eyes, reading by lamplight like that," he would say. "Come on, come to the tavern with us. There is a girl who works there. Julia, she has got the most beautiful smile. You should see her." But Marcus would shake his head. "I need to understand this," he would say, pointing to whatever text he was reading. "I need to really understand it, not just memorize it." Gaius would shrug and go off with Titus, leaving Marcus to his studies. But there was no ill will in it. They each had their own approach to the apprenticeship, their own way of learning. As the months passed, Marcus gradually settled into the routine. The work that had seemed overwhelming at first became familiar. He learned the geography of Rome, could navigate from the office on the Aventine Hill to the various aqueduct sites around the city. He learned the personalities of the different engineers and staff, knew who to ask for what kind of help, who would be patient with questions and who would be irritated by them. He learned the social dynamics of the apprentices, the unspoken pecking order, the expectations and the boundaries. He made mistakes, of course. Everyone did. There was the time, about 4 months into his apprenticeship, when he misread a measurement by a factor of 10, calculating that a channel would carry 10 times as much water as it actually could. Priscus caught the error when reviewing Marcus's work, and he was not pleased. "Come here, boy," he said, his voice stern. Marcus approached nervously. "Look at this calculation," Priscus said, pointing to Marcus's wax tablet. "You are telling me that a channel 1 meter wide and 1 meter deep, flowing at this velocity, will carry this much water." He pointed to the number Marcus had written. "Does that seem reasonable to you?" Marcus looked at the number and suddenly realized his error. "No, sir," he said quietly. "That is too much. I made a mistake in the calculation." "You certainly did," Priscus said. "And if this had been a real project, if you had specified a channel size based on this calculation, what would have happened?" Marcus thought about it. "The channel would be too small, sir. It wouldn't be able to carry the required amount of water. The project would fail." "Exactly," Priscus said. "The project would fail. Resources would be wasted. People would be disappointed, and your reputation would be damaged. This is why you must check your work. Every calculation, every measurement, every specification. Check it once, then check it again, because mistakes have consequences, real consequences that affect real people." Marcus felt his face burning with embarrassment and shame, but he also felt grateful that Priscus had caught the error, had taken the time to explain why it mattered, had turned it into a teaching moment rather than just punishment. "Yes, sir," Marcus said. "I understand. I'll be more careful." "See that you are," Priscus said, his tone softening slightly. "You have talent, boy. You have the mind for this work. But talent without discipline is worthless. Learn to be methodical. Learn to be thorough. Those habits will serve you well throughout your career." Marcus never forgot that lesson. From that day forward, he developed a practice of always checking his calculations at least twice, of asking himself whether his results made sense, whether they were reasonable. It was a habit that stayed with him for the rest of his life. Think about that for a moment. A mistake made at age 13, caught and corrected by a good teacher, leading to a lifetime habit of careful work. That is the power of education, of mentorship. The lessons we learn early, especially the ones that come with some emotional weight, some embarrassment or difficulty, those tend to stick with us. There were lighter moments too. Marcus remembered the first time he successfully completed an independent measurement task. Priscus had sent him to measure the flow rate of a particular fountain in the Forum Manum. It was a standard procedure. You would divert the fountain's water into a container of known volume and time, how long it took to fill. Then you could calculate the flow rate. Marcus had watched others do this many times, but this was the first time he was doing it alone without supervision. He was nervous, worried that he would make some mistake. But he followed the procedure carefully. He found a suitable container, measured its volume precisely. He diverted the fountain flow into it. He timed the fill using a water clock, one of the standard timekeeping devices of the era, a vessel with a small hole that allowed water to drip out at a steady rate, with marks on the inside to show the passage of time. He performed the measurement 3 times to ensure consistency. The results were close, within the expected margin of error. He calculated the average and converted it to the standard units used for flow measurements. When he returned to the office and reported his results to Priscus, the senior engineer nodded approvingly. "Good work," he said simply. But to Marcus, those 2 words felt like the highest praise. He had done it. He had completed a task independently and done it correctly. He was learning. He was becoming competent. As Marcus progressed through his first year of apprenticeship, he began to participate in small repair projects. These were minor things, fixing cracks in channels, replacing worn sections of pipe, clearing blockages. But they gave him experience with the practical aspects of construction and repair. He learned how to mix mortar to the right consistency. He learned how to apply it properly, ensuring good adhesion and a waterproof seal. He learned how to cut and shape stone using techniques his father had taught him years ago, but now applying them in a new context. He learned how to work with lead pipe, how the pipes were cast in long sections, how they were joined together, how they were secured and supported. He learned how to work as part of a team, coordinating with other workers, communicating clearly, helping when help was needed, and staying out of the way when he would just be underfoot. The social aspect of the work was important. Construction projects involved many people, workers from different trades, with different skills and temperaments. Being able to work with people, to understand their perspectives, to communicate effectively, these were essential skills for an engineer. Marcus learned that a good engineer wasn't someone who stood apart and gave orders. A good engineer worked alongside his men, understood what they were doing, respected their expertise, listened to their concerns. The workers knew practical things that you couldn't learn from books. Things about how materials behaved, about techniques that worked and techniques that didn't, about the little tricks and workarounds that made difficult jobs easier. An engineer who was too proud to learn from his workers was an engineer who would make avoidable mistakes. Marcus also learned about the economics of construction. Priscus would sometimes involve the apprentices in reviewing bids from contractors, teaching them to analyze costs, to understand where money was being spent, to identify when a bid seemed too high or suspiciously too low. A bid that is too low is just as concerning as one that is too high, Priscus explained. If it is too high, the contractor might be trying to overcharge you. But if it is too low, the contractor might be planning to cut corners, to use inferior materials, or rush the work. Either way, you'll have problems. He taught them to read contracts, to understand the terms and conditions, to know what recourse you had if a contractor failed to deliver what was promised. He taught them about the legal framework governing public works, the laws about water rights, about property access for construction, about liability for damages. Engineering isn't just technical, Priscus would say. It is also legal, economic, political. A successful project requires managing all these dimensions, not just solving the technical problems. According to Professor Roger Ulrich, who has studied Roman construction management, this kind of comprehensive training was characteristic of the best Roman engineering education. The Romans understood that building large public works required not just technical skill, but also administrative ability, legal knowledge, and political savvy. The engineers who rose to prominent positions were those who could navigate all these aspects effectively. As Marcus's second year of apprenticeship began, he was given more responsibility. He was now allowed to assist directly with surveying work, not just watching but actually taking measurements under supervision. He participated in design work, helping to draw up plans for small projects, calculating dimensions and material requirements, preparing the specifications that would guide construction. He was developing the professional skills and judgment that would eventually allow him to work independently. He was also developing physically. The work was demanding, and Marcus, who had been a somewhat skinny boy when he arrived in Rome, was becoming stronger, developing the wiry endurance that came from daily physical labor. Walking long distances to inspect aqueducts, climbing up and down access shafts, working in cold water, handling heavy materials. All of this built strength and stamina. By the time he was 15, Marcus was no longer the uncertain new boy. He was an experienced apprentice, someone the younger apprentices looked to for guidance, someone the senior engineers trusted with real responsibilities. He still had much to learn, years of learning ahead of him, but he had established himself as serious and capable. One of the most important developments in Marcus's third year came when he began to specialize. While all the apprentices learned the basics of aqueduct engineering, individuals would often develop particular interests or aptitudes. Some gravitated towards surveying and route planning. Others preferred structural design, working on the arcades and tunnels. Still others focused on hydraulic calculations, flow rates, and pressure analysis. Marcus found himself particularly interested in the problem of water quality and contamination. He had noticed during the various inspections he participated in that water quality varied significantly between different aqueducts and even between different sections of the same aqueduct. Some water was crystal clear and cold, delicious to drink. Other water had a slight cloudiness or a mineral taste, or occasionally an unpleasant smell. Why? What caused these differences? Priscus encouraged his interest. Water quality is crucial, he said. People notice. If the water tastes bad, they complain. If it makes them sick, you have a serious problem. Understanding what affects water quality, that is valuable knowledge. Marcus began to study the issue systematically. He would collect water samples from different points in the aqueduct system and observe their characteristics. He would note the colour, the clarity, the taste, any smell. He would try to correlate these observations with what he knew about the sources and the channels. He learned that water from springs in limestone hills tended to be very pure, the limestone acting as a natural filter. Water from rivers, by contrast, could be contaminated by runoff, by animal waste, by whatever was happening upstream. He learned that water quality could degrade as it travelled through the aqueduct if contamination entered through cracks in the channel, or if the channel materials reacted with the water in undesirable ways. He learned that temperature affected water quality. Colder water tended to taste better and stay fresh longer. Warmer water was more prone to developing algae and bad tastes. He learned that settling tanks, those intermediate basins where water was allowed to slow down and sediment would sink to the bottom, played an important role in maintaining quality, but they only worked if they were properly designed and regularly cleaned. Marcus began to develop ideas about how to improve water quality through better design and maintenance. He wrote up his observations and thoughts in a series of notes which he nervously showed to Priscus. The senior engineer read them carefully, then nodded thoughtfully. "Good work," he said. "You are thinking like an engineer, observing systematically, trying to understand causes, proposing solutions. Keep this up, develop these ideas further. This could be valuable. Ayasparu. That encouragement meant everything to Marcus. He wasn't just learning to follow procedures. He was learning to think independently, to observe and analyze and create new knowledge. That was what real engineering was about. Think about this for a moment. Here is a teenager, 15, 16 years old, conducting what amounts to scientific research, studying a practical problem, making observations, developing hypotheses, testing ideas. We sometimes imagine that this kind of systematic investigation is a modern development associated with the scientific method as it emerged in the 17th centuries. But people have been thinking systematically about practical problems for as long as there have been practical problems to solve. The Romans didn't have the formal scientific framework we use today, but they had keen observation, logical thinking, and a willingness to learn from experience. Marcus's 4th year brought an important milestone. He turned 16, and Priscus decided it was time for him to experience his first major field project. This would be the Aqua Marcia inspection with Veiento that we talked about earlier, that 2-week journey walking the entire 91 kilometers of the Marcia, documenting problems, learning what large-scale infrastructure inspection actually involved. But what I didn't tell you before were some of the specific daily experiences of that journey, the texture of what it was like to spend 2 weeks living and working in that intense, focused way. Let me take you there now, day by day, so you can really feel what it was like. Day 1 began at the Springs, 40 kilometers east of Rome, in the beautiful green hills of the Anio Valley. Marcus and Veiento arrived there in the morning, having ridden out from Rome the day before and spent the night at a small inn in a nearby town. With them came the 4 assistants who would handle measurements and note-taking, and a pack mule carrying their equipment and supplies. The spring houses were impressive structures, small stone buildings built around the sources to collect the water cleanly and protect it from contamination. There were 3 primary springs feeding the Marcia, and each had its own spring house with settling basins and gates that controlled flow into the main channel. Veiento spent the entire first day inspecting these source structures meticulously. He checked the masonry of the spring houses for any cracks or deterioration. He examined the settling basins, looking for accumulated sediment, checking that the overflow mechanisms were working properly. He tested the gates, opening and closing them to ensure they moved smoothly and sealed completely. He walked around the areas surrounding the springs, looking for any signs of contamination sources, animal waste, agricultural runoff, anything that might threaten water quality. And he took flow measurements, carefully timing how long it took to fill a container of known volume, calculating the output of each spring. Marcus watched all of this, taking notes, asking questions when appropriate, learning Veiento's systematic approach. Start at the source, Veiento explained. Always start at the source. Understand what you are working with. How much water are the springs producing? What quality? Are the collection structures functioning as designed? Once you understand the source, then you can work downstream and understand what you are seeing. By late afternoon, Veiento was satisfied with the source inspection. They made camp nearby, the assistants setting up simple tents while Veiento and Marcus reviewed the day's findings. The springs were producing about 212,000 cubic meters per Dalton Y Veiento calculated, which was actually above the historical average. Good news. But there was some sediment accumulation in the settling basins that should be cleaned out. Not urgent, but it should be scheduled. That evening, sitting around their campfire after a simple meal of bread and cheese and wine, Veiento talked about the history of the Marcia. Built in 1944 BC, he said. More than 200 years ago. Think about that. This aqueduct has been bringing water to Rome for more than 2 centuries. It was ancient when I was born. It'll still be here long after we're gone if we do our jobs properly. That is what I want you to understand. Marcus, we're not building for ourselves. We're not building for our lifetimes. We're building for centuries. Every decision we make has to consider that time scale. Marcus listened, staring into the fire, letting the words sink in. building for centuries. It was an awesome responsibility when you really thought about it. Day 2, they began walking the aqueduct itself, starting from the outlet of the primary settling tank, where the 3 spring sources combined into the main channel. For the first several kilometers, the channel ran in an open trench, about 1 meter wide and 1.5 meters deep, the water flowing smoothly along the gentle gradient. Walking this section was pleasant. The weather was mild, spring sunshine, green hills around them. Veiento would stop frequently, examining the channel walls, looking for cracks, checking the waterproofing. Marcus learned to spot the things Veiento was looking for: a slight discoloration that might indicate water seeping through, a change in the sound of the flow that might indicate an obstruction. Small things, subtle signs, but important. They found their first problem around midday. A section of channel wall had a crack, not large, maybe 10 centimeters long, but definitely growing. You could see where it had been repaired previously, old mortar filling what had probably been a smaller crack, and now the crack had extended beyond the repair. This is common, Veiento said. Ground settling. Temperature changes causing expansion and contraction, the constant pressure of water. It all takes a toll. Stone cracks, you can't prevent it entirely. What you can do is catch it early and repair it before it becomes a serious leak. He had one of the assistants make a detailed note of the location and the size of the crack, sketching it so that repair crews would know exactly what they were dealing with. Then they moved on. By late afternoon, the aqueduct entered its first tunnel section, disappearing underground. This was where the work became more difficult and uncomfortable. There was a vertical access shaft, every 60 meters or so, stone-lined shafts about 1 meter in diameter, descending 20 to 30 meters to the tunnel level. Veiento climbed down the first shaft, using the iron rungs set into the wall, his oil lamp hanging from his belt. Marcus followed, trying not to show how nervous he was. It was dark down there, except for the small circles of light from their lamps. The walls were close, rough stone, damp and cold. At the bottom they could hear the water flowing in the tunnel, a rushing sound echoing in the confined space. They waded into the tunnel, the water coming up to their knees, cold enough to make Marcus gasp. The tunnel ceiling was low, about 2 meters high, forcing them to walk with heads slightly bowed. Veiento moved slowly, carefully, holding his lamp to illuminate the walls and ceiling, examining every meter of the tunnel. "See there," he said, pointing to a spot on the ceiling. Marcus looked and saw what Veiento was indicating, a dark stain on the rock, and water dripping from a small crack. "That is groundwater infiltration," Veiento said. "There is another water source above us, probably a small spring or underground stream. It is seeping through the rock and dripping into our channel. This is bad for 2 reasons. First, it is contaminating our pure spring water with groundwater of unknown quality. Second, it is slowly eroding the rock around the crack, making the crack bigger. Eventually, this could become a serious structural problem." One of the assistants following behind them made a note of the location and the nature of the problem. This would require excavation from above to find and divert the source, significant work. They spent hours working through that tunnel section, stopping at each access shaft to catch their breath, to warm up a bit in the spring sunshine before descending into the next section. By the time they emerged from the tunnel in late afternoon, Marcus was exhausted and chilled to the bone. His feet were numb from the cold water. His back ached from walking bent over. His eyes burned from staring into the darkness by lamplight. But Veiento seemed barely affected. "You'll toughen up," he said, seeing Marcus's condition. "First time is always the hardest. Your body will adapt." They made camp near the tunnel exit, and one of the assistants built a good fire. Marcus sat as close to it as he could, trying to get warm, trying to stop shivering. He thought about home, about his father's house in Ver'ai, about warm meals and dry clothes and comfortable beds. This was harder than he had imagined, but he also felt a sense of accomplishment. He had done it. He had worked through that entire tunnel section, had kept up with Veiento, had done his job. He was learning what the work really required. That night, Veiento talked about tunnel construction, explaining how the Romans excavated these underground channels through miles of rock, how they maintained alignment and gradient in the darkness, how they dealt with unexpected obstacles like the groundwater they had found that day. The men who built this tunnel 200 years ago, Veiento said, they faced the same problems we're finding now. They encountered groundwater, just like we did today. But they couldn't eliminate the source, so they did the best they could, lining the tunnel with stone, creating drainage channels to handle the infiltration. It worked well enough for a long time, but now the problem is getting worse. That is the nature of infrastructure. Problems that were manageable when a structure is new become serious as it ages. That is why maintenance is crucial. You have to stay ahead of deterioration. Day 3 brought more tunnel sections, more cold water, more darkness. Marcus's body was already starting to adapt as Veiento had predicted. He was less shocked by the cold water, more accustomed to the confined space. But the work was still difficult. They found more contamination sources, 5 more drips from the tunnel ceiling in various locations. They found a section where the channel had partially collapsed, rocks fallen from the ceiling into the water, reducing the flow area. They found mineral deposits building up on the channel walls, not yet severe enough to significantly affect capacity, but something that would need to be addressed eventually. Each problem was documented, location noted, severity assessed, recommendations made. By the 4th day, they had fallen into a rhythm. Wake at dawn, eat a quick breakfast, begin walking and inspecting. Work through the morning, stop briefly for a midday meal, continue through the afternoon. Make camp in the evening, review the day's findings, discuss what they would likely encounter the next day. Eat dinner around the fire, talk about engineering, about Rome, about life, sleep. Do it again. Marcus found himself looking forward to the evening conversations with Veiento. The senior engineer had worked on aqueducts for 30 years, and he had an inexhaustible store of stories and knowledge. He talked about projects he had worked on, problems he had solved, mistakes he had made, and what he had learned from them. He talked about the politics of public works, how to navigate the competing demands of different interest groups, how to maintain professional standards while satisfying officials who might not understand technical requirements. He talked about the satisfaction of the work, the feeling of knowing that your efforts were keeping a vital system functioning, serving hundreds of thousands of people. People take it for granted, Veiento said one evening. They turn on a fountain and water flows, and they don't think about it. They don't think about the 40 kilometers of channel bringing that water from the mountains. They don't think about the inspections and repairs that keep that channel functioning. They don't think about the engineers who designed it or the workers who maintain it, and that is as it should be. Good infrastructure is invisible, it just works. But we know what it takes, and we have to find our satisfaction in that knowledge, in doing the work well, not in public recognition. Marcus absorbed these lessons. This was more than technical training. This was learning how to think about a career, how to find meaning in work that would mostly go unrecognized. By the 6th day, they reached the section where the aqueduct emerged onto arcades for its approach to Rome. This was a dramatic change from the underground sections. Now the channel rode high above the ground, carried on tall stone arches, the water flowing in an elevated channel, visible and impressive. Walking these arcade sections was different from the tunnels. Instead of being underground in the dark and cold, they were out in the sunshine and fresh air. But it came with its own challenges. To inspect the actual water channel, they had to climb up the arcades, using external stone staircases in some places, rickety wooden ladders in others. At the top, there was usually a narrow walkway alongside the channel, sometimes with a low wall, sometimes with nothing but a long drop on one side. You had to move carefully, watch your footing, not look down if heights bothered you. Marcus discovered that heights did bother him, rather a lot actually. The first time he climbed up to the top of an arcade section about 20 meters above the ground and looked down, he felt his stomach lurch. Veiento noticed his hesitation. "Don't think about the height," he said. "Focus on the work. Look at the channel, not at the ground. Keep your attention on what you are doing and you'll be fine." It helped, somewhat. Marcus learned to keep his eyes on the channel, on the stonework he was examining, on the water flowing past. He learned to move deliberately, one foot carefully in front of the other, never rushing. And gradually the fear became manageable. Not gone, but not paralyzing either. They found different problems in the arcade sections. Here it wasn't groundwater infiltration, but rather structural issues. Cracks in some of the piers caused by settling foundations or by the freeze. Thaw cycle of water getting into small cracks and expanding when it froze in winter. Mortar joints that had eroded, needing repointing. Expansion joints which allowed the structure to flex with temperature changes, that had become clogged with debris and weren't functioning properly. And in one section they found something more serious. A pier that had developed a noticeable lean, a clear indication that the foundation was failing. This was dangerous. If that pier failed completely, it could bring down a section of the arcade, cutting off water supply and potentially injuring anyone who happened to be nearby. Veiento spent a long time examining that pier, measuring the lean, checking the foundation, assessing the severity. "This needs immediate attention," he finally said. "We'll send word back to Rome today. Request an emergency repair crew." This can't wait for the regular repair schedule. He had one of the assistants ride back to Rome that evening with an urgent message. The rest of them continued their inspection, but Veiento's mind was clearly preoccupied with that failing pier. That night he talked about the responsibility they carried. "When we find something like that pier," he said, "we're making a judgment about risk. How serious is it? How quickly might it fail? What is the consequence if it does fail? Get that judgment wrong, and people could die. That is a heavy responsibility. You have to be conservative, have to err on the side of caution, but you also can't cry wolf over every minor issue, or people will stop taking your warnings seriously. Finding that balance, that comes with experience." Marcus listened and understood that this was one of the crucial skills he would need to develop. The technical knowledge was important, but so was the judgment, the ability to assess situations and make sound decisions with incomplete information and uncertain outcomes. By the 10th day they were nearing Rome, working through the final sections of the aqueduct where it entered the city. These sections were complex, with the channel splitting into multiple branches to serve different districts, with settling tanks and distribution basins, with maintenance structures and control gates. Veiento inspected all of it systematically. He checked the distribution gates, making sure they opened and closed smoothly, making sure the flow control mechanisms worked properly. He checked the settling tanks, examining the baffles that slowed water flow to allow sediment to sink, checking the sluice gates that allowed tanks to be drained for cleaning. He measured flow rates at different points to verify that water was being distributed as intended. By the 12th day, they were finished. 12 days, 91 kilometers, every accessible section of the Aqua Marcia inspected and documented. More than 40 problems identified, ranging from minor maintenance needs to that serious structural issue with the pier. A comprehensive picture of the aqueduct's condition assembled. They rode back to the office on the Aventine Hill, dirty and tired but satisfied. Veiento immediately began writing his formal report, documenting findings and making recommendations. Marcus helped, organizing the notes, preparing sketches and diagrams. Over the next several days they compiled everything into a comprehensive document that would guide the repair work. When the report was complete and submitted to the Curator Aquarum, Veiento called Marcus aside. "You did good work on this inspection," he said. "You kept up, you paid attention, you learned. I am going to recommend that you be assigned to help oversee the repairs. You found the problems. You should be part of fixing them. That is how you really learn." Marcus felt a surge of pride and gratitude. This was recognition, real recognition from someone whose opinion mattered. He had proven himself. He was becoming a real engineer. Think about what that inspection journey meant for Marcus's development. 2 weeks of intensive work under the direct mentorship of an experienced engineer. 2 weeks of facing physical challenges, overcoming discomfort and fear, learning what the job really required. 2 weeks of seeing problems in context, understanding not just what was wrong but why it mattered and how it could be fixed. That kind of immersive hands-on learning is incredibly valuable. You can't get it from books or lectures alone. You need to experience it, to do the work, to struggle with the difficulties, to feel the weight of responsibility. Modern engineering education recognizes this, which is why internships and co-op programs are considered so important. The principles haven't changed. Real expertise requires real experience. Now let me tell you about the repair project that followed that inspection, because this is where Marcus learned some of the hardest lessons of his career. The lessons about human cost, about the weight of responsibility for other people's safety and lives. The curator Aquarum Marcus Coxius Nerva approved a major repair project for the Aqua Marcia based on Viento's report. 200,000 sesterces were allocated, a substantial budget. A workforce of 50 men was assembled, drawn from various sources. Some were employees of the curator Aquarum's office, skilled workers who did this kind of work regularly. Others were contractors, specialists in particular trades. And some were day labourers, men who showed up each morning hoping for work, taking whatever jobs were available. Viento was put in charge of the overall project, and Marcus, now 17 years old, was assigned as his assistant, responsible for supervising certain sections of the work. It was the first time Marcus had real supervisory authority, the first time men would be working under his direction. He felt the weight of it immediately. The project was organised into multiple work crews, each tackling different repair tasks. One crew worked on sealing the contamination sources in the tunnels, excavating from above to find and divert the groundwater sources. Another crew worked on the structural repairs to the arcades, rebuilding the failing pier and repairing cracks in others. Another crew worked on cleaning and repointing mortar joints. Another handled miscellaneous small repairs, the dozens of minor issues that had been documented. Marcus was assigned to oversee the arcade repair crew, 15 men working on the structural issues. His foreman was an experienced mason named Lucius Nonius, a man in his 40s who had worked on aqueducts for 20 years. Nonius knew his trade thoroughly, knew how to work with stone, how to build and repair arches and piers. But he was also gruff and sometimes dismissive of the young engineer who was supposed to be supervising him. The first day of work, when Marcus came to the site and began to explain what needed to be done, Nonius interrupted him. "Boy, I was building arches before you were born," he said. "I know what needs doing here. You just stay out of our way and let us work." Marcus felt his face flush with embarrassment and anger, but he remembered Priscus's teachings about working with craftsmen, about respecting their expertise, about not being too proud to learn from them. "You are right," Marcus said, keeping his voice level. "You know this work better than I do, but I am responsible for ensuring that the repairs meet the specifications, that they're done properly, that they're safe for the workers and safe for the long-term integrity of the structure. I am not here to tell you how to do your job. I am here to make sure that what gets done is what needs to be done. Can we work together on that basis?" Nonius studied him for a moment, then nodded grudgingly. "All right," he said, "fair enough. What do you need from me?" "I need you to explain to me how you are planning to approach the repairs," Marcus said. "Show me your plan. If I have concerns, I'll raise them." "If you have concerns about the specifications, you raise them. We talk it through. We agree on the approach, then you do the work. Does that work for you?" "It does," Nonius said, and his tone was slightly less hostile. They worked out a plan for the pier repair. The pier was leaning because its foundation had failed, probably because it had been built on soil that had later settled or washed away. To fix it properly, they would need to stabilize the foundation, which meant excavating around it down to bedrock or solid soil, then building a new foundation base. While that was being done, the pier itself would need to be temporarily supported to prevent further movement. Nonius explained how he would do this. Wooden scaffolding and braces to hold the pier in its current position, careful excavation around the base, shoring up the hole as they dug to prevent collapse, new foundation work in layers, allowing each layer to set properly before adding the next. Finally, rebuilding the lower portion of the pier where it had been damaged by the foundation failure. It would take about 3 weeks, Nonius estimated, weather permitting, and assuming they didn't encounter unexpected problems. Marcus thought through the plan, trying to identify any issues. "What about safety?" he asked. "This pier is unstable. What if it shifts while your men are working around it? What if the scaffolding fails?" "It is a risk," Nonius admitted. "We'll brace it as well as we can. We'll watch for any signs of movement. But yes, there is risk. There is always risk in this kind of work." Marcus thought about Priscus's lectures on construction safety, about the engineer's responsibility to minimize risk to workers. "Can we add extra bracing?" he asked. "More scaffolding than you would normally use just to be safe?" Nonius shrugged. "We could. It'll take more time to set up and more materials. But if you are willing to authorize the cost, sure, we can do that." Marcus was willing to authorize the cost. The budget would absorb it, and if it made the work safer, it was worth it. "Do it," he said. "I'd rather spend the money and have everyone go home safely." Nonius nodded, and Marcus thought he saw a glimmer of respect in the older man's eyes. The work began. Marcus visited the site daily, checking progress, inspecting the quality of the work, watching for problems. The excavation around the pier proceeded slowly, carefully. The new foundation work was done in stages, just as Nonius had outlined. Everything seemed to be going well. The incident happened on the 8th day of the project. Marcus wasn't at the site when it occurred. He was at another site, checking on a different repair crew. He got the news from a messenger who came running, out of breath and pale. "Accident at the arcade repair." The messenger gasped. "Man fell. Badly hurt." Marcus's stomach dropped. He ran to the site, his mind racing. Who fell? How bad was it? What happened? When he arrived, he found a scene of controlled chaos. Most of the workers had stopped and were clustered in groups, talking in low, shocked voices. Nonius was kneeling next to a man who lay on the ground, clearly in agony. It was one of the workers, a man whose name Marcus knew was Marcus Nonius, the foreman's cousin. He had been working on the scaffolding around the pier when one of the wooden planks had broken, and he had fallen about 5 meters to the ground below. The fall had broken his left leg badly. Marcus could see the unnatural angle, could see bone protruding through the skin. The man was conscious, but in terrible pain, groaning and occasionally crying out. There was blood, though not as much as Marcus had feared. Nonius looked up as Marcus approached. "We've sent for a medicus," he said. "Not much else we can do until he gets here, but it is bad. That leg is badly broken." Marcus knelt down next to the injured man, not sure what to do, but feeling like he should do something. "Help is coming," he said, trying to sound reassuring. "You are going to be all right." But he didn't know if that was true. Broken bones could heal sometimes, but infection was common, and a break this severe, with the bone piercing the skin, that was dangerous. The medicus arrived about 20 minutes later, an old Greek physician who served the local neighborhood. He examined the injury, his face grim. "I need to set this bone," he said. "It is going to hurt. Hold him down." Several men held the injured worker while the medicus manipulated the broken bone, trying to align the fragments, trying to push the protruding bone back under the skin. The man screamed, a horrible sound that Marcus would hear in his nightmares for weeks afterward. Finally, the medicus was done. He splinted the leg with wooden boards and wrapped it tightly with linen bandages. "Keep him still," he said. "Keep the wound clean. I'll check on him tomorrow. But I'll be honest with you, that is a bad break. Even if it heals, he'll likely be lame, and infection is a real risk. If infection sets in, I may have to amputate to save his life." Marcus felt sick. This man, Marcus Nonius, he was about 30 years old. He had a wife and 2 young children. Marcus knew because Lucius Nonius had mentioned them, and now, because of an accident that happened while working on a project Marcus was supervising, his life might be destroyed. Even in the best case, a lame leg, he might not be able to work as a labourer anymore. How would he support his family? Marcus helped arrange for the injured man to be carried home. He visited the man's family that evening, bringing money from the project budget to help with the medical expenses and lost wages. The wife, a young woman with a baby in her arms and a toddler clinging to her skirts, was frightened and trying to be brave. "Will he be all right?" she asked Marcus. "Will he be able to work again?" "I don't know," Marcus said honestly. "The medicus is doing everything he can. We'll help with expenses. Make sure you have what you need, but I can't promise you that everything will be fine. I am sorry. I am so sorry this happened." That night, Marcus couldn't sleep. He kept thinking about the accident, about that scream when the medicus set the bone, about the wife's frightened face, about the children who might grow up with a disabled father or no father at all if infection took him. He kept wondering if there was something he could have done to prevent it. He had ordered extra scaffolding, extra bracing, but maybe that wasn't enough. Maybe he should have inspected the scaffolding planks more carefully. Maybe he should have required even more extensive safety measures. Vianto, when Marcus told him about the accident the next day, was sympathetic but also pragmatic. "Accidents happen," he said. "We do what we can to minimize risk, but we can't eliminate it entirely. You ordered extra bracing. That was good. But a wooden plank broke. That is bad luck, not your fault. The question is, can you learn anything from this? Can you do anything differently to prevent similar accidents in the future?" Marcus thought about it. "I could inspect materials more carefully," he said. "Check the scaffolding planks to make sure they're sound, not rotten or cracked." "Good," Vianto said. "Do that. Make it a standard procedure. Inspect scaffolding before it is used. That is a lesson learned from this accident, a way to make future work safer." Marcus implemented the new procedure immediately. He personally inspected all the scaffolding planks at all the work sites, had workers replace any that showed signs of rot or damage. It didn't undo the accident that had already happened, but maybe it would prevent a future one. Marcus Nonius, the injured worker, survived. His leg did heal, after a fashion, though the medicus's prediction proved accurate. The leg was shorter than the other, badly scarred, and it pained him to walk on it. He couldn't do the physical labour he had done before. Lucius Nonius, the foreman, found him a job as a watchman at a construction yard, work that was less physically demanding and that he could do despite the lame leg. It was lower pay than he had made as a labourer, but it was something. Marcus arranged for a payment from the project fund to the family, a one-time payment of 500 sesterces, substantial money, enough to help them through the difficult transition. It wasn't required by any law or regulation. It was simply something Marcus felt was right. Lucius Nonius, when Marcus told him about the payment, gripped the young engineer's hand. "You are a good man," he said, his voice rough with emotion. "You didn't have to do this. Thank you. That was the first of the accidents. Unfortunately, it wasn't the last." The second happened 6 weeks later, at one of the tunnel sites where a crew was working to seal one of the contamination sources. The worker's name was Titus Valerius, a man in his early 20s, one of the day labourers who had been hired for the project. To reach the contamination source, they had excavated a vertical shaft from the surface down to the tunnel level, about 25 metres. The shaft was supposed to be shored up with wooden timbers to prevent collapse, and the first 20 metres had been properly shored. But in the last 5 metres, near the bottom where the shaft met the tunnel, the shoring hadn't been completed yet. The plan was to finish it the next day. Titus Valerius was at the bottom of the shaft, working in the tunnel, when the unsupported section collapsed. Tons of earth and rock fell into the shaft, burying him instantly. By the time the other workers could dig him out, he was dead, suffocated by the earth. Marcus was at the site within an hour of the accident. He climbed down an adjacent shaft and saw the collapsed section, saw the rescue crew digging frantically, hoping against hope that Titus might still be alive, even though everyone knew it was almost certainly too late. They recovered the body late that afternoon. Titus Valerius was unmarried, but he had parents, an aging father and mother who depended on his wages to survive. Marcus went to see them that evening, brought them the terrible news, tried to offer condolences that felt utterly inadequate. He was a good boy, the mother said, weeping. He worked hard, he was going to get married next year. He had a girl, Julia, they were planning a life together, and now he is gone. What are we going to do? How will we live? Marcus arranged for another payment from the project fund, tried to help them however he could, but no amount of money could undo the loss of their son. This accident, Marcus felt even more responsible for. The shaft should have been completely shored before workers were allowed in the tunnel below. That was the procedure, but the foreman for that site, in a rush to keep the work on schedule, had let workers start in the tunnel while the shoring was still incomplete. Marcus should have caught that. He should have been inspecting more carefully. He should have enforced the procedures more strictly. Veiento conducted a formal investigation of the accident. He interviewed all the workers on the site, examined the collapsed shaft, reviewed the work plans. His conclusion was that the foreman had violated safety procedures and was at fault. The foreman was dismissed from the project, but Veiento also noted in his report that oversight had been insufficient. The supervising engineer should have ensured that safety procedures were being followed, the report stated. The supervising engineer was Marcus. Marcus accepted the criticism. He had failed in his responsibility. He resolved to be more vigilant, to inspect every site more frequently, to enforce procedures more strictly, even if it slowed down the work. Better to be slow and safe than fast and deadly. The third death happened near the end of the project. A worker named Lucius Didius was helping to move a large block of stone using a crane, a wooden framework with ropes and pulleys that allowed heavy loads to be lifted and moved. The stone block was being lifted to the top of an arcade where it would be used to repair a damaged section. The crane was a standard design, one that had been used successfully many times, but this time one of the ropes broke. Marcus was never able to determine exactly why. Perhaps the rope was worn and should have been replaced. Perhaps it was overloaded. Perhaps there was a flaw in one of the fibers that made it fail under stress. Whatever the reason, the rope broke, and the heavy stone block fell. Lucius Didius was standing in the wrong place. The stone struck him, crushing his chest. He died within minutes, blood frothing from his mouth as his crushed lungs failed. Marcus had been at that site that day, had been standing perhaps 20 meters away when it happened. He saw the stone fall, saw it hit Lucius, heard the sickening impact, saw the man go down. He ran over, but there was nothing to be done. Lucius was already beyond help. 3 deaths. 3 men who had come to work on the project Marcus was helping to supervise, and who had gone home to be buried instead. 3 families devastated, 3 lives cut short. Marcus was only 17, and the weight of this responsibility was crushing. After Lucius Didius died, Marcus went to Veiento and asked to be taken off the project. "I can't do this anymore," he said, and he was ashamed to find that there were tears running down his face. 3 men have died. I can't carry this responsibility. I am not ready for this. I am not good enough at this. Veiento listened, then shook his head. "No," he said, "you don't get to quit. Do you know why? Because quitting would be the easy thing, the thing that would make you feel better, but it wouldn't help the workers who remain. It wouldn't help the next project. What you need to do is learn from this, figure out how to be better, how to make the work safer, take the pain of these deaths and turn it into determination to prevent future deaths. That is what being an engineer means. It means carrying the weight of responsibility and not running from it." Marcus wanted to argue, wanted to insist that he wasn't capable of this. But he looked at Veiento's face and saw that the older engineer was serious, was asking him to be stronger than he felt. So Marcus stayed on the project, and he threw himself into safety improvements. He personally inspected every piece of equipment before it was used. He checked every rope, every scaffold plank, every shoring timber. He insisted on extra precautions even when workers grumbled that it was slowing down the work. He held safety meetings every morning, reminding workers of procedures, asking them to watch out for each other. According to Dr. Lynn Lancaster, the level of attention to construction safety varied widely in the Roman world. Some projects were managed carefully, with real efforts to protect workers. Others treated workers as expendable, accepting high accident rates as inevitable. The difference often came down to individual managers and engineers who cared enough to make safety a priority. Marcus became one of the engineers who cared. For the rest of his career, safety would be one of his highest priorities. He would never stop seeing the faces of Titus Valerius, Marcus Nonius, Lucius Didius. He would never forget the families they left behind, and he would do everything in his power to prevent other workers from suffering the same fate. The Aquamarcia repair project was eventually completed successfully. The contamination sources were sealed. The structural repairs were done. The water quality improved. The flow rate increased. By every technical measure, it was a success. But for Marcus, the project would always be shadowed by those 3 deaths, by the knowledge that men had died while working on something he was responsible for. Think about what that does to a person. Marcus was still essentially a teenager, and he was carrying responsibility for other people's safety, other people's lives. And when things went wrong, when men died, he had to carry that weight. It aged him in a way. He became more serious, more careful, less quick to laugh. But it also deepened him, gave him a sense of moral gravity that would serve him well in the years ahead. In our modern world, we have elaborate safety regulations, legal frameworks for worker protection, agencies that enforce safety standards. The regulations exist because people fought for them, often in response to terrible accidents and tragedies. The protections we have now were built on the suffering of workers in earlier generations. Marcus didn't have those regulations. He had to create his own standards based on his own values and his own painful experience. The principles he developed, caring for worker safety, inspecting equipment, enforcing procedures, holding people accountable for violations, those principles remain relevant today. Let me take you forward now a few years to Marcus's time as deputy curator, when he was responsible for the entire water system of Rome, because this position gave him the opportunity to deal with a wide variety of challenges, and I want to tell you about some of the specific incidents that tested his abilities and taught him important lessons. One incident I remember particularly well from the historical records involved a major pipe break in the winter of 74 AD. It happened in the Subura, one of Rome's most densely populated districts, a neighborhood of tall apartment buildings where thousands of people lived in crowded condition. A major supply pipe, a lead pipe about 30 centimeters in diameter, bringing water from the Aqua Julia to a distribution basin in the Subura, suddenly burst. One moment, there was normal water pressure and flow. The next moment, a fountain of water was shooting up out of the ground, flooding the street, pouring into ground floor shops and apartments. Marcus got the report in the middle of the night, a messenger pounding on his door, shouting that there was an emergency in the Subura. Marcus dressed quickly and rode to the scene. What he found was chaos. Water was still pouring from the break, a geyser shooting 3 meters into the air. The street was flooded ankle deep. People were trying to move their possessions to higher ground, shouting and confused. The first priority was to stop the flow. The pipe break was in the middle of a section with no convenient shoot-off valve nearby. To stop the flow, they would have to close the main supply valve for this entire section of the Aqua Julia, which would cut off water to not just the Subura, but to several other neighborhoods as well. Marcus made the decision to do it. "Close the main valve," he ordered. "Cut off the supply. We need to stop this flooding before we do anything else." A crew ran to the valve station and closed the valve. The pressure dropped, and the geyser subsided to a trickle, then stopped. Now Marcus could assess the damage. The pipe had burst because it had frozen. It was winter, and there had been several nights of hard frost. The pipe was buried, but not very deeply, and in this location the ground didn't provide enough insulation. Water in the pipe had frozen, expanded and cracked the lead. The pipe would need to be excavated and replaced, which would take at least a day, possibly two. In the meantime, thousands of people would be without water. Marcus organized the response. He had crews begin excavating the broken pipe so repairs could start. He arranged for water wagons to bring water from other parts of the city to supply the affected neighborhoods, at least for drinking and cooking. He posted notices explaining what had happened and when service would be restored, and he initiated a study of the entire water distribution system to identify other pipes that might be vulnerable to freezing so that preventive measures could be taken before the next winter. The repair took 36 hours. For that time, Marcus barely slept, spending his time at the worksite coordinating crews, checking progress, dealing with complaints from residents and officials. Finally, the new section of pipe was installed and tested. The valve was reopened. Water flowed again. Marcus went home and slept for 12 hours straight. But before he slept, he had already started making notes on what could be learned from this incident. The result was a new policy. All water pipes in shallow installations would be inspected before winter, and vulnerable sections would be wrapped with insulating materials or buried deeper. It was a simple measure, but it prevented many future freeze-related breaks. Think about this incident in terms of emergency response. Marcus had to make quick decisions with incomplete information. He had to manage multiple priorities simultaneously, stopping the immediate damage, beginning repairs, providing temporary service to affected residents. He had to communicate clearly with workers, with officials, with the public. He had to stay calm under pressure, and after the crisis was over, he had to learn from it to implement changes that would prevent similar crises in the future. These are the same skills that emergency managers need today. The technology has changed, but the fundamental challenges of managing a crisis remain the same. Another incident from Marcus's time as deputy curator involved political pressure and the need to maintain technical standards against demands for shortcuts. A wealthy senator named Lucius Salvius Otho wanted a private water connection to his new villa. This was legal and common. Wealthy Romans could purchase the right to a private water connection, paying a fee to the curator, Aquarium's office. The fee was based on the size of the pipe, which determined how much water the connection could draw. Standard pipe sizes were defined by regulation, and the fees were set accordingly. Senator Otho wanted a larger pipe than the standard sizes allowed. He wanted to install gardens with elaborate fountains at his villa, and he needed more water than the standard connection would provide. He approached Marcus, explaining what he wanted, expecting that his senatorial rank would ensure cooperation. Marcus explained the regulations. The pipe sizes are standardized, Senator, for good reason. They ensure that private connections don't draw more than their fair share of water, which would reduce pressure for other users. I can approve a connection at any of the standard sizes, but I can't approve a non-standard size without authorization from higher authority. Then get authorization, Otho said, his tone making it clear he expected this to be a formality. I am willing to pay an appropriate fee. This shouldn't be a problem. Marcus could have simply passed the request up to Cerealis, let the curator Aquarium make the decision, but he felt it was important to maintain the technical standards, not to create exceptions for wealthy or politically powerful people. Senator, with respect, the issue isn't just about the fee, Marcus said. It is about maintaining equitable water distribution. If I approve an oversized connection for you, I create a precedent. Other wealthy people will expect the same privilege, and each oversized connection reduces the pressure and flow available for everyone else, including the public fountains that ordinary people depend on. I don't think that is good policy. Otho's face darkened. Are you refusing my request? I am asking you to work within the standard regulations, Marcus said, trying to keep his voice respectful but firm. You can have a standard connection, which will provide a substantial amount of water, or if you need more, you can purchase 2 standard connections which would be within the regulations. "This is ridiculous," Otho said. "I will take this to the Emperor if necessary. You are being unreasonably rigid." "That is your right, Senator," Marcus said. "I am simply trying to do my job, which is to manage Rome's water supply fairly and sustainably." Otho did indeed complain to higher authorities. He spoke to Cerealis, who called Marcus in to explain his position. Marcus laid out his reasoning, explained the precedent that would be set, the impact on water distribution, the importance of maintaining standards. Cerealis listened and then supported Marcus's position. "The standards exist for good reasons," Cerealis said. "We'll offer Senator Otho the option of 2 standard connections. If that is not acceptable to him, that is unfortunate, but we're not making special exceptions." Otho eventually accepted the 2-connection solution, though he was not pleased about it. But Marcus had won a victory for principle over political pressure, and it established his reputation as someone who would stand firm on technical standards even when it was politically difficult. According to Professor Catherine Rinn, this kind of political negotiation was a constant feature of managing Roman water infrastructure. There were always pressures to make exceptions, to grant special privileges, to bend the rules for powerful people. Curators and engineers who could navigate these pressures while maintaining technical standards were valuable and respected. Marcus developed a reputation for being fair but firm. He would work with people, find solutions to their needs when possible, but he wouldn't compromise on the fundamental principles of equitable and sustainable water management. That reputation served him well throughout his career. Another type of challenge Marcus faced regularly was the need to innovate to find better ways of doing things. One innovation he implemented involved the inspection and maintenance scheduling system. As I mentioned earlier, Marcus had established a systematic inspection program, with different teams responsible for different sections of the aqueduct system. But he found that the scheduling was inefficient. Teams would sometimes overlap, inspecting adjacent sections at different times when it would make more sense to coordinate. Inspections were scheduled based on calendar dates, but some sections needed more frequent inspection than others based on their condition and their importance. Marcus redesigned the system to be more efficient and more targeted. He created a classification scheme for different sections of the aqueducts, rating them based on age, condition, importance to overall system function, and accessibility for repairs. Sections that were in poor condition, or that were critical to system function, or that were difficult to repair, those got more frequent inspections. Sections that were in good condition and less critical got less frequent inspections. He coordinated inspection schedules geographically so that teams would inspect adjacent sections during the same time period, reducing travel time. He implemented a record-keeping system that tracked the history of each section, what problems had been found in past inspections, what repairs had been done, so that inspectors could focus on known trouble spots. The result was a more efficient use of inspection resources and better early detection of problems. The innovation might sound simple and obvious, but it required careful thought and systematic organization. It required collecting data, analyzing it, identifying patterns, designing a better system, implementing it, and then refining it based on experience. This was engineering applied to management and organization, not just to physical structures. Think about this in modern terms. We use data-driven approaches to maintenance scheduling all the time now. We track equipment condition. We use predictive analytics to identify when failures are likely. We prioritize maintenance based on criticality and condition. The principles Marcus was developing in the 1st century AD are the same principles we use today. The tools have changed dramatically, but the underlying logic remains the same. Marcus also worked on innovations in water quality management. Building on his early interest in this topic, he implemented a regular water quality testing program. Samples would be collected from various points in the system: the source, springs, intermediate settling tanks, distribution points in the city, and tested for clarity, taste, odor, temperature. When quality problems were detected, Marcus's team would investigate to find the cause. Was it contamination entering through a crack? Was it algae growth in a settling tank that wasn't being cleaned frequently enough? Was it mineral deposits affecting water chemistry? Each problem had a specific cause and a specific solution. By systematically tracking water quality and investigating problems, Marcus was able to maintain high standards and catch issues before they became serious. He also experimented with improvements to settling tank design. The standard settling tanks used at that time were simple basins where water flow was slowed, allowing sediment to sink to the bottom. But Marcus thought they could be more effective. He designed tanks with internal baffles, walls that forced water to flow in a serpentine path through the tank, increasing the time water spent in the tank and allowing more sediment to settle out. He tested this design at several locations and found that it significantly improved sediment removal compared to the standard design. Gradually, as existing tanks needed to be rebuilt or new ones were constructed, the improved design became standard. These might seem like small innovations, incremental improvements rather than revolutionary breakthroughs. But infrastructure improvement is mostly incremental. You make things a little better, a little more efficient, a little more reliable, year after year. Over time, those small improvements accumulate into significant advancement. Marcus understood this. He didn't expect to revolutionize water engineering. He expected to make steady, careful improvements, to leave the system better than he found it. That was his goal, and he achieved it. During his years as deputy curator, from 71 AD to 81 AD, Marcus oversaw the completion of the Aqua Augusta Vespasiana, managed the routine maintenance and operation of Rome's entire water system, responded to numerous emergencies, implemented systematic improvements to inspection and maintenance procedures, and mentored a generation of younger engineers who learned from his example. It was a decade of intense, demanding work, but it was also a decade when Marcus truly came into his own as an engineer and as a leader. He developed confidence in his judgment, in his ability to solve complex problems, in his capacity to manage large systems and teams of people. He learned to balance technical excellence with political necessity, to maintain standards while navigating bureaucratic pressures, to innovate while respecting established procedures. He learned to carry the weight of responsibility, to make difficult decisions, to live with the consequences of his choices, and he learned to find satisfaction in the work itself, in the knowledge that he was serving millions of people, keeping essential systems functioning, contributing to the life of the greatest city in the world. Think about what 10 years of work like this does to a person. Marcus was 24 when he became deputy curator. He was 34 when he stepped down from the position. Those are formative years, the years when you go from young adulthood to full maturity. Marcus spent those years at the heart of Rome's infrastructure management, dealing with every kind of challenge that could arise, developing the expertise and judgment that would serve him for the rest of his career. By the time he left the position and began his career as a consulting engineer, Marcus had become one of the most knowledgeable water engineers in the empire. He had worked on every major aqueduct serving Rome. He had dealt with every type of problem that could affect an aqueduct: structural failures, water quality issues, capacity constraints, maintenance challenges, political pressures. He had designed and built a major new aqueduct. He had managed complex organizations and large projects. He had trained and mentored younger engineers. He had earned the respect of his peers and the trust of officials. And he had done all of this while maintaining his integrity, his commitment to technical excellence, his concern for worker safety, his dedication to equitable and sustainable water management. These weren't just professional accomplishments. They were evidence of character, of the kind of person Marcus had become. Sound familiar? This is what a successful career in any demanding profession looks like. Years of hard work, of learning from experience, of taking on increasing responsibility, of developing expertise and judgment. Years of facing challenges and solving problems, of making mistakes and learning from them, of carrying the weight of responsibility and finding meaning in service to others. The details change from profession to profession, from era to era. But the fundamental arc, the development from novice to expert, from student to master, from follower to leader, that arc remains constant. It is how humans develop mastery in any complex domain. It takes time, it takes dedication, it takes good teachers and hard-won experience. Marcus had all of these things, and the result was a career that mattered, work that made a difference, a life well lived in service to something larger than himself. Let yourself think about that as you settle deeper into comfort. Think about what it means to develop real expertise, real mastery of something difficult and important. Think about the satisfaction that comes from solving hard problems, from building things that last, from knowing that your work matters, even if it goes unrecognized by most people. That is what Marcus found. That is what gave his life meaning. And in our own very different world, with our own very different challenges, we can find the same kind of meaning in doing difficult work well, in serving others, in building and maintaining the systems that make civilized life possible. Rest now. Let these stories settle in your mind. Let yourself feel the weight of Marcus's experiences, the challenges he faced, the lessons he learned, the person he became. Tomorrow will bring its own challenges. But tonight, just rest, and remember that you are part of a long tradition of people trying to do difficult work well, trying to serve others, trying to build something that will last. Sleep well, friends. The water still flows, carried in channels that were built with knowledge and skill and care. The work continues, generation after generation, and you are part of that great ongoing work in whatever way you contribute to building and maintaining our shared world. Sweet dreams.